Picture a place where the hands of a clock don't move where past, present, and future don't follow one another, but instead exist all at once. It sounds like something out of science fiction, but what if I told you such places aren't just fantasy? They might be hiding in plain sight, scattered throughout our universe in the most extreme and mysterious corners of space. This is the world of timeless regions, areas where time, as we understand it, simply doesn't flow. It's a concept that stretches our imagination, challenges our intuition, and invites us to look at reality in a completely new light. We begin with a thought from physicist Julian Barbour, who once said, "Time is nothing but a measure of change. Where nothing changes, time does not flow." That single idea opens the door to some of the most profound questions in modern science and philosophy. What happens in a place where change itself grinds to a halt? Can time truly stand still? And if so, what would that even look like? In this video, we're going to explore exactly that: the cosmic anomalies and theoretical wonders where time loses its grip. From the crushing depths of black holes to the mind-bending possibilities of wormholes and parallel universes, we'll venture into realms that defy everything we think we know about time. Why does any of this matter? Because understanding timeless regions doesn't just satisfy scientific curiosity, it shakes the very foundation of how we perceive reality. It asks us to reconsider what it means to exist, to experience, and to remember. It touches on questions that have puzzled philosophers for centuries and now sit at the forefront of cutting-edge physics. This journey will take us through startling theories, eerie phenomena, and breathtaking implications, all designed to expand your perspective and leave you with a deeper sense of wonder about the cosmos. So get ready, we're about to travel where time has no meaning and the rules of the universe are rewritten. But what exactly do we mean when we say a place is timeless? In our daily lives, time feels absolute and constant. It's the steady rhythm of seconds ticking by, the sun rising and setting, the undeniable progression from past to future. We plan our days, celebrate birthdays, and measure our lives by this unyielding flow. Yet, out in the cosmos, this familiar experience of time is not a universal rule. It's more like a local custom, one that doesn't apply everywhere. A timeless region is a zone where this progression breaks down entirely. It's not that time slows down, it's that the very concept of before and after loses its meaning. In these extraordinary places, the arrow of time, that one-way direction from order to disorder, can bend, twist, or even snap. This radical idea is supported by some of the greatest minds in physics. The renowned theorist Carlo Rovelli, for instance, proposes that time is not a fundamental building block of the universe but an emergent property. It's something that arises from the interactions of countless quantum particles, much like temperature emerges from the jiggling of atoms. In most places, this emergence creates the smooth, flowing time we know. But in areas of extreme physics, like the heart of a black hole, those underlying interactions could become so warped that time, as a coherent phenomenon, simply ceases to exist. It doesn't freeze, it evaporates. To understand how this is possible, we need to look at two key concepts from Einstein's theory of relativity: event horizons and gravitational time dilation. An event horizon is like a point of no return, a one-way boundary in space. The most famous example is the edge of a black hole. Once anything, including light, crosses this invisible threshold, it can never come back. For an observer watching from a safe distance, time appears to stand still for an object falling toward a black hole. It would seem to slow down, becoming redder and fainter until it effectively freezes at the event horizon, never quite crossing from our perspective. Meanwhile, gravitational time dilation describes how time itself passes at different rates depending on the strength of the gravitational field. Your head actually ages slightly faster than your feet because it's farther from Earth's center of gravity. Now amplify that effect to the extreme environment near a neutron star or a black hole, and the difference becomes staggering. Time doesn't just slow. In the most intense gravitational fields, its passage can become infinitely stretched. The real-world implications of this are as fascinating as they are bizarre. Imagine two astronauts. One stays in orbit around Earth, while the other ventures close to a massive object like a black hole. Due to time dilation, the astronaut near the black hole would age far more slowly than their partner. Upon returning, they might find that what felt like a few years for them was decades or even centuries for everyone else. This isn't just theoretical. Our global positioning system, GPS, has to account for these relativistic effects. The satellites in orbit experience time ever so slightly faster than clocks on the ground, and if their software didn't correct for this, your navigation would be off by several miles within minutes. This foundational understanding of how gravity warps time is the key that unlocks the door to even stranger possibilities, like the potential for time travel and the true nature of the most infamous timeless region in the cosmos. Now, let's venture closer to this ultimate cosmic mystery, the black hole singularity. Picture the most extreme environment imaginable, a place where gravity has won a total victory over every other force in the universe. At the very center of a black hole, all the matter that has ever fallen in is compressed into an infinitely tiny point, a singularity of infinite density. According to the equations of general relativity, at this precise spot, the curvature of spacetime becomes infinite, and our conventional understanding of time completely shatters. It doesn't just slow down, it stops. The very concepts of before and after have no meaning here because the progression of events ceases to exist. This isn't merely a pause, it's a fundamental breakdown of the framework we use to describe reality itself. From the perspective of someone watching from a safe distance, the story is equally bizarre. Imagine you are observing a brave astronaut on a one-way mission into a black hole. As they approach the event horizon, that point of no return, you would see something strange happen. Their spacecraft would appear to slow down, its image becoming redder and fainter due to the extreme gravitational redshift. From your vantage point, the astronaut would never actually cross the horizon. Instead, they would seem to freeze there, their image etched onto the edge of the black hole for all eternity, as time for them appears to stand still from your frame of reference. Yet, for the astronaut themselves, the journey continues. They would cross the event horizon without any dramatic sensation, at least initially, and continue to fall inward, experiencing time in a seemingly normal way until the tidal forces of the black hole's gravity, the difference in pull between their head and feet, become overwhelming. This is the heart of the paradox. How can two realities be true at once? For the outside universe, time for the astronaut has stopped. For the astronaut, time continues to flow until their inevitable encounter with the singularity. This contradiction forces physicists to confront a deep flaw in our understanding: general relativity, which predicts the frozen observer and the singularity, and quantum mechanics, which insists that information cannot be destroyed, are fundamentally at odds here. This is where Stephen Hawking's revolutionary work enters the picture. He discovered that black holes are not entirely black. Due to quantum fluctuations near the event horizon, they slowly emit radiation and can eventually evaporate. This Hawking radiation suggests that information about what fell into the black hole might not be lost forever, but could somehow be encoded in this radiation. adding a profound layer of quantum weirdness to the gravitational paradox. The existence of a singularity is essentially physics' way of saying, "I don't know." It's a sign that our current theories have reached their limits. In that point of infinite density, the laws of physics as we know them break down. Concepts like space and time, which form the very stage upon which the universe plays out, cease to have any definition. This isn't just an academic curiosity. It challenges our most basic notions of cause and effect. If time can stop, then what does causality mean? How can an effect follow a cause if there is no time for it to happen in? The black hole singularity is the ultimate cosmic riddle, a place that exists beyond the realm of known science, pushing us to develop a new, deeper theory, a theory of quantum gravity, that can finally reconcile these opposing views and tell us what truly happens when time itself comes to an end. But if the singularity challenges our understanding of time's flow, the next paradox challenges the very nature of time's existence. This is the concept of eternalism and the block universe. Instead of imagining time as a river flowing from the past to the future, eternalism proposes that all moments in time, your birth, your reading of this sentence, and every event yet to come, already exist with equal reality. Think of the entire cosmos not as a changing, evolving thing, but as a single, unchanging four-dimensional block. In this model, the past isn't gone and the future isn't unborn. They are simply other locations within this vast, static structure, much like how Paris and Tokyo are different locations in space. This view finds a strange home in timeless regions, where the absence of a flowing now suggests there might not be a privileged present moment anywhere. This radical idea has deep philosophical roots. Early in the 20th century, philosopher J.M.E. McTaggart argued that time is ultimately an illusion because our descriptions of events in time are inherently contradictory. We can place an event in a sequence, like saying World War II happened after World War I, but we can also assign it a tense, calling it a past event. McTaggart claimed this dual nature creates an inconsistency that cannot be resolved, leading him to conclude that time is not fundamentally real. While this remains a topic of fierce debate, it finds a curious echo in modern physics, particularly in the bizarre phenomenon of quantum entanglement. Experiments have repeatedly shown that two entangled particles can influence each other instantaneously, regardless of the distance separating them. This spooky action at a distance, as Einstein called it, seems to defy the speed of light limit and suggests a connection that operates outside our conventional understanding of time and space, hinting at a deeper, timeless layer of reality where such correlations are just built-in facts. The implications of a block universe are nothing short of staggering for our perception of self and freedom. If every moment is equally real and fixed within the block, then the entire timeline of your life is already written. The version of you that took a specific job, met a specific person, or is watching this video right now is just one slice of a predetermined whole. This raises profound and unsettling questions about free will. Is our feeling of making choices just an illusion, a necessary byproduct of our consciousness moving through the frozen landscape of the block? Or does free will operate on a level that this four-dimensional perspective cannot capture? It forces us to confront whether destiny is a real concept and what it truly means to have agency in a universe where the future might already be just as concrete as the past. To truly grasp this, consider a powerful analogy. Imagine the entire history of the universe is a finished book. You, right now, are a reader holding a bookmark at a single page. You experience the story linearly, page by page, believing that the pages behind you are finished and the pages ahead are unwritten. But in the block universe model, the entire book already exists, complete and unchangeable. Your consciousness is simply the spotlight of your attention, moving from chapter to chapter. If you could step outside of this book, as if observing a timeless zone, you would see all pages, all events from the Big Bang to the heat death of the universe laid out simultaneously. Your birth, the rise and fall of civilizations, and every star that will ever be born would all be equally present and accessible. This perspective doesn't make our lived experience any less vivid or meaningful, but it fundamentally shifts our understanding of reality, suggesting that our linear journey is merely a single, limited perspective on a much grander and more mysterious whole. While the block universe model presents a static, all-encompassing view of reality, there exists another theoretical construct that twists time into something far more dynamic and paradoxical: the wormhole. Often called an Einstein-Rosen bridge, a wormhole is a hypothetical tunnel through the very fabric of space-time, a shortcut that could connect two incredibly distant points in the universe, or even more astonishingly, two completely different moments in time. The mathematics of general relativity doesn't forbid their existence. In fact, the equations naturally produce solutions that describe these bizarre structures. But with their potential for time travel comes one of the most famous and troubling paradoxes imaginable, a problem that threatens the very logical consistency of cause and effect. This is the grandfather paradox, a thought experiment that has fueled countless science fiction stories but poses a serious question for physicists. Imagine you built a time machine, perhaps using a stable, traversable wormhole. You travel back to a time before your grandfather had met your grandmother. Through some action, perhaps accidental, you prevent them from ever meeting. This would mean one of your parents was never born, and consequently, you would never be born. But if you were never born, how could you have existed to travel back in time and alter those events in the first place? The result is a logical inconsistency, a loop of cause and effect that has no beginning and no end, creating a reality that seems to contradict itself. It's a classic example of what physicists call a closed time-like curve, a path through spacetime that loops back on itself, allowing travel into one's own past. Renowned physicists like Kip Thorne have spent decades studying these possibilities, not to write fiction, but to explore the true boundaries of physical law. The existence of such paradoxes suggests that something must prevent them from happening, a concept sometimes called the chronology protection conjecture. One compelling resolution comes from the quantum world. The moment you try to create a scenario that would lead to a paradox, quantum mechanics might intervene. For instance, as you step out of your time machine with a plan to disrupt the past, a strange series of coincidences could occur: a slip on a banana peel, a sudden equipment failure, or an unexpected intervention that perfectly prevents you from ever succeeding. The universe, through the bizarre rules of quantum probability, might simply not allow a paradoxical event to take place, ensuring its own logical consistency. Another potential resolution lies in the dizzying possibility of the multiverse. In this view, your journey back in time wouldn't actually be a journey into your own past, but a jump into a parallel universe that is nearly identical to your past. In this new branch of reality, your actions would create a new, divergent timeline. You might prevent that version of your grandfather from meeting your grandmother, and in that universe you would never be born. But that's okay, because the original you, the one who stepped into the time machine, came from a different, unaltered timeline. Your own existence and personal history remain perfectly intact, safe in your home universe. The paradox is avoided because the cause and effect are not locked in a tight loop within a single timeline, but are instead spread across multiple, parallel realities. What makes these ideas so captivating is that they are not mere fantasy. They are serious investigations grounded in the same equations that accurately predict the orbit of Mercury and the bending of light around the Sun. They push our understanding of relativity to its absolute limits, revealing where it might break down and require a union with quantum mechanics. A timeless wormhole, a tunnel where the normal flow of time breaks down, could be a place where cause and effect become tangled in an endless loop, challenging our most fundamental notion of sequence and forcing us to reconsider the very nature of reality itself. These are the frontiers of theoretical physics, where the line between the impossible and the possible is blurred, and where the answers might just redefine everything we think we know about time. Yet if the singularities within black holes are mysterious, they pale in comparison to the ultimate singularity, the one that is believed to have given birth to everything. The Big Bang Theory, the cornerstone of modern cosmology, tells us that our entire universe expanded from an initial state of unimaginable density and temperature. But what was that state like? According to the mathematics, it was a true singularity, a point where all the mass and energy of the cosmos was concentrated into an infinitely small, infinitely dense speck. And in that condition, the rules change completely. The equations of general relativity break down, and with them, our understanding of time itself. This leads us to one of the most profound and baffling paradoxes of all, the idea that time, the very framework of our existence, may have had a definitive beginning. The staggering implication is that there was no before the Big Bang. Asking what happened before the universe began is like asking what is north of the North Pole. The question itself may be meaningless because time, as we understand it, is a property of our universe. It came into existence with the universe. Before that, if we can even use the word before, there was no time. There was no space, there was just nothing, or perhaps something so fundamentally different from our reality that we lack the words or concepts to describe it. This confronts us with the ultimate existential question: how can something come from nothing? How did a universe of galaxies, stars, planets, and life emerge from a state of timelessness? Cosmologists like Alexander Vilenkin have spent their careers grappling with this very puzzle. One compelling model suggests that our universe could be the product of a spontaneous quantum fluctuation. In the weird world of quantum mechanics, empty space is never truly empty. It's a seething foam of virtual particles that constantly pop into and out of existence, borrowing energy from the vacuum for fleeting moments. Now, imagine this happening on a cosmic scale. Vilenkin and others propose that the entire universe could have tunneled into existence from literally nothing, a quantum fluctuation in a primordial void where the concepts of before and after held no sway. In this model, the Big Bang wasn't an explosion in space and time, but the very origin of space and time. This idea naturally bridges the gap between science and philosophy, even touching on theology. For centuries, the question of a first cause has been central to many philosophical and religious traditions. The concept of a creator or an unmoved mover is an attempt to address the paradox of beginnings. Modern cosmology doesn't provide a definitive answer, but it offers a fascinating scientific narrative that resonates with these ancient questions. It suggests that the laws of physics as we know them, cause and effect, the arrow of time, did not apply in that initial timeless state. They emerged along with the universe, freezing out of a more fundamental and perhaps timeless reality during the first fractions of a second of the Big Bang. This paradox serves as a powerful reminder of the limits of our conventional understanding. Our brains are wired to think in terms of cause preceding effect, of a linear progression of events. The notion of a true beginning with no prior cause is incredibly difficult to accept because it runs counter to all our lived experience. Yet, the evidence from the cosmic microwave background radiation, the faint afterglow of the Big Bang, and the observed expansion of the universe strongly points to this reality. It hints that the deepest mysteries of existence lie in that first moment, in the transition from timelessness to time, and that comprehending it fully may require a complete revolution in physics, one that successfully unites gravity with quantum mechanics. While the Big Bang represents a fiery beginning bursting with activity and the potential for time's birth, the cosmos might be headed toward a far quieter, and in many ways more chilling, conclusion. This is the concept of heat death, a final state of maximum entropy where the universe reaches a perfect and unchanging equilibrium. It's a destination not of violent collapse, but of an endless, silent fade into uniformity. In this state, the very engine of change runs out of fuel, and with it the arrow of time. That relentless push from past to future may simply vanish, leaving behind a cosmos where time itself becomes meaningless. To understand why, we need to grasp the deep connection between time and disorder, a concept physicists call entropy. Imagine a fresh deck of cards, neatly organized by suit and number. This is a state of low entropy, a condition of high order. Now shuffle that deck thoroughly. The cards become randomized, disordered, a state of high entropy. The crucial point is that this process only goes one way. You can easily turn an ordered deck into a disordered one, but you cannot turn a shuffled deck back into its pristine, factory order state without exerting a significant amount of energy and effort. The universe operates on the same principle. It naturally evolves from states of order to states of disorder. Entropy always increases. This inevitable rise in disorder is what gives time its direction. We remember the past as being more ordered and expect the future to be more disordered. It's why an ice cube melts in a warm room but never spontaneously reforms from the puddle, and why we grow older instead of younger. Now project this process out across trillions upon trillions of years. All the stars will eventually burn out, their fuel exhausted. All matter may decay into radiation, and through the relentless expansion of the universe driven by dark energy, this energy will be spread so thin across the vastness of space that the temperature everywhere approaches absolute zero. There will be no hot spots and no cold spots, no energy gradients whatsoever. Without a difference in energy, no work can be done, no stars can form, no chemical reactions can occur, no motion can be sustained. Every process that could possibly happen will have already happened. The universe will be a static, ultra-cold, and utterly uniform soup of particles and radiation, completely devoid of any interesting activity. It will have reached its maximum possible entropy, a state of final, eternal equilibrium. This is where the paradox for time emerges. If time is indeed nothing but the measure of change, as Julian Barbour suggested, then in a universe where absolutely nothing changes, time loses all meaning. There is no before or after because every moment is identical to the last. The arrow of time, which was defined by the increase of entropy, disappears because entropy can no longer increase. It has already reached its maximum value. Physicists like Sean Carroll describe this as the ultimate end of history, not with a bang, but with a timeless whimper. It's a bleak but intellectually fascinating finale where the cosmos becomes a featureless, eventless void forever. To make this abstract concept more personal, consider a thought experiment. Imagine you were somehow still conscious in this far future era of heat death. What would you experience? The answer is nothing. No events would occur to mark the passage of time. Your thoughts themselves, which are electrochemical processes requiring energy, would be impossible. You wouldn't feel bored or peaceful. You wouldn't feel or perceive anything at all. There would be no aging, no memory formation, no sense of duration, just a single, static, and eternal instant. Your existence would be frozen, not in the sense of being cold and still, but in the sense of being completely divorced from the flow of time. This profound paradox forces us to consider that time may not be a fundamental feature of the universe, but an emergent property that arises from thermodynamic processes. It exists only as long as there is a universe out of balance, striving toward equilibrium. Once that balance is achieved, time, like a story that has been fully told, simply ends. But if the immense scales of cosmic heat, death feel remote and abstract, the next paradox brings our exploration of timelessness down to the smallest imaginable level, into the bizarre and bustling world of the quantum vacuum. We often think of empty space as just that, empty, a void, a nothingness. But quantum mechanics reveals this to be a profound illusion. What we perceive as a vacuum is in reality a seething, bubbling, and hyperactive sea of potentiality, where the very concepts of something and nothing become blurred, and where time itself behaves in ways that defy all common sense. This frenetic activity is known as vacuum fluctuation. Due to the fundamental uncertainty principle in quantum mechanics, empty space can never be perfectly still. Instead, pairs of virtual particles, a particle and its antimatter counterpart, constantly and spontaneously pop into existence, borrowing energy from the vacuum for an almost incomprehensibly short moment, only to annihilate each other and vanish back into nothingness almost immediately. These are not particles in the traditional sense. They are fleeting disturbances in quantum fields, ghostly appearances that are here one instant and gone the next. And the time scales involved are almost beyond human comprehension. The typical lifetime of one of these virtual pairs is on the order of the Planck time, which is about 10 to the power of negative 43 seconds. To put that number in perspective, there are more Planck times in a single second than there have been seconds since the Big Bang itself. At this unimaginably tiny scale, our smooth, continuous notion of time begins to completely break down. Physicists working on theories of quantum gravity, like Lee Smolin, propose that time might not be a fundamental, flowing river, but rather something that emerges from a more basic, underlying reality. At the Planck scale, time could be granular or discrete, meaning it is made of indivisible little chunks, the smallest possible units of time, much like a digital video is made of individual frames. Between these frames, between one Planck time and the next, there might be no in-between at all. In those gaps, the concept of temporal flow may have no meaning, creating a kind of timeless granularity that forms the foundation of our perceived reality. This leads to a stunning paradox that challenges our understanding of cause and effect. Consider the strange case of these virtual particles. They appear and disappear without a clear cause. They violate the classical law of conservation of energy, but they do so for such a vanishingly brief instant that the uncertainty principle allows it. In this bizarre quantum arena, the clean, linear arrow of time, where cause always precedes effect, becomes fuzzy and ill-defined. An effect, the appearance of a particle, doesn't seem to have a clear cause other than the raw probabilistic nature of the universe itself. It's as if the vacuum is constantly trying out different possibilities, flickering through potential realities in these timeless intervals, and what we perceive as stable, continuous time is just the averaged out result of this unimaginably rapid and timeless underlying activity. This isn't just a theoretical curiosity. We can actually observe the effects of this quantum frenzy. One famous demonstration is the Casimir effect. If you take two perfectly smooth, neutral metal plates and place them incredibly close together in a vacuum, they will be gently pulled toward each other. Why? Because the space between the plates is so narrow that it restricts the kinds of virtual particles that can pop into existence there. The space outside the plates, however, remains full of this quantum activity. The greater pressure from the outside literally pushes the plates together. This measurable force is direct experimental proof that the vacuum is not empty, but is instead alive with transient, timeless energy. This paradox fundamentally alters our view of reality, revealing that what we call empty space is the most active and strange place of all, a foundational layer of existence where time itself is born from a timeless, probabilistic dance. But if the quantum world reveals a vacuum teeming with timeless potential, our own minds offer a more immediate and personal gateway to these strange states. We don't need a spaceship or a particle accelerator to experience a distortion in time. It happens to us all the time, quite literally. Our perception of time is not a perfect, objective recording of the universe's clock, but a fluid, malleable construction built by our brains. In moments of intense focus, sheer terror, or profound peace, the steady tick-tock of the second hand can warp, stretch, or even vanish completely, creating a powerful psychological experience of timelessness that eerily mirrors the cosmic phenomena we've been exploring. Neuroscientists like David Eagleman have dedicated their careers to unraveling this mystery. Through ingenious experiments, such as dropping volunteers from a great height onto a safety net, his team has shown how the brain's internal clock can be dramatically altered by extreme circumstances. In those terrifying seconds of freefall, subjects consistently reported that time seemed to slow to a crawl. Eagleman's theory suggests this isn't because the brain processes information faster in a crisis, but because it lays down a much denser memory log during a novel, high adrenaline event. When you look back on that fall, the sheer volume of new memories makes it feel like the event lasted much longer than it actually did. It's a trick of recollection, a post-processing effect that creates the powerful illusion of dilated time. This subjective manipulation of time isn't limited to fear. The opposite end of the spectrum offers an even more profound glimpse into timelessness. Athletes and artists often describe being in the zone, a state of flow where their actions and awareness merge completely. In this state, self-consciousness falls away, and with it, the constant mental chatter that normally marks the passage of time. A musician lost in a performance might feel like only a minute has passed, only to look up and see that an hour has evaporated. There is no past or future in the flow state. There is only the perfect, absorbing present. This sensation is strikingly similar to the experiences reported by seasoned meditators who, through deep practice, can reach states of consciousness where the concept of duration disappears entirely, leaving only a vast, undifferentiated awareness they often describe as the eternal now. Perhaps the most compelling modern examples come from those who have literally left our planet. Astronauts frequently return to Earth with stories that go beyond the technical details of their mission, speaking of a profound cognitive shift known as the overview effect. Floating in the cupola of the International Space Station, gazing down at the delicate, jewel-like Earth against the infinite black velvet of space, many report a complete dissolution of their normal sense of time. The awe-inspiring vista, combined with the novel environment of microgravity, can short-circuit the brain's usual time-keeping mechanisms. They describe a sense of profound connection to the cosmos and a feeling that they are witnessing something eternal and unchanging, even as they orbit the planet every 90 minutes. Their experience suggests that timelessness isn't just a neurological glitch. It can be triggered by a direct, overwhelming encounter with the scale and beauty of the universe itself. This creates a fascinating and deeply personal paradox. The timeless regions inside a black hole or at the birth of the universe are physically remote, accessible only through mathematics and theory. Yet the feeling of timelessness, the actual lived experience of it, is something we can access within our own consciousness. This bridges the vast gap between the outer cosmos and our inner worlds. It suggests that time may not be an absolute dictator of reality, but a framework that our minds impose upon it, a useful tool for navigating the world that can, under the right conditions, be temporarily set aside. The fact that we can experience states so reminiscent of these cosmic paradoxes hints that the universe's deepest secrets about time might not only be written in the stars, but also encoded within the very structure of our awareness, waiting to be unlocked by a moment of focus, a glimpse of awe, or a breath of stillness. Yet this strange warping of time is not confined to the far reaches of the cosmos or the pages of a physics textbook. It's a phenomenon that operates silently and precisely right here, right now, in the technology many of us rely on every single day. The global positioning system, that network of satellites guiding our cars and phones, would be utterly useless if it weren't for our understanding of gravitational time dilation. Each of those satellites carries an incredibly precise atomic clock, and according to Einstein's theory, two specific relativistic effects are constantly acting upon them. First, because they are moving at tremendous speeds relative to observers on the ground, special relativity dictates that their clocks should tick slightly slower. But second, and more significantly for this paradox, because they are orbiting about 20,000 kilometers above the Earth, they are in a much weaker gravitational field. General relativity tells us that this weaker gravity makes their clocks tick faster than identical clocks on the surface. These two effects don't cancel each other out. The gravitational effect is actually stronger. The net result is that the clocks on the satellites gain about 38 microseconds every single day. That might sound like an almost laughably small amount of time, but in the world of satellite navigation, where determining your position depends on measuring the exact travel time of signals traveling at the speed of light, those microseconds are catastrophic. Light travels nearly 300 meters in a single microsecond. If the engineers who designed the GPS system did not deliberately program the satellite clocks to run slightly slower before launch to correct for this effect, the entire system would accumulate errors of over 10 kilometers per day, rendering it completely inaccurate within minutes. Your navigation app would be hopelessly lost almost immediately. This isn't a theoretical adjustment. It's a daily, practical application of Einstein's radical ideas, a constant correction for the fact that time itself does not pass at the same rate everywhere. This leads us directly to the heart of the paradox. Imagine two highly diligent clockmakers, one stationed on the surface of the Earth and the other on board a GPS satellite. Both set their identical, perfect atomic clocks to the exact same time. After a year, they compare results. The clockmaker on the satellite will find that his clock has run faster. It shows that more time has elapsed compared to the clock on Earth. Now, here's the crucial question: which clock is correct? The astonishing answer is that both are right. From the perspective of the clockmaker on Earth, his clock is measuring time perfectly normally. From the perspective of the clockmaker on the satellite, his clock is also measuring time perfectly normally. There is no universal now. Each observer's measurement of time is correct for their own location and state of motion. This is the essence of relativity. There is no single, privileged frame of reference. Time is not absolute, it is personal. To push this to its ultimate extreme, consider the famous twin paradox, but with a gravitational twist. Suppose one twin decides to live her life on the surface of a dense neutron star, while the other chooses to reside on a small, low-gravity moon. After several decades, they reunite at a neutral location. The twin from the neutron star would be significantly younger than her sibling. the crushing gravity of her home would have literally slowed down her biological processes, her experiences, and her aging relative to her counterpart in a weaker gravitational field. They shared the same beginning, but their paths through the warped geometry of spacetime were different, leading to a measurable physical difference in their ages. Their individual experiences of the passage of time were both entirely real and valid, yet they led to undeniably different outcomes. This profound realization forces us to abandon the comforting Newtonian idea of a master clock for the universe. Time is not a river flowing at the same rate for everyone. It is more like a vast, varied landscape. It stretches and compresses, speeds up and slows down, depending on where you are and how you are moving. The GPS system is our everyday proof, a constant, invisible reminder that the fabric of reality is far more malleable and strange than our everyday senses suggest. This relativity of time isn't an obscure detail. It is a fundamental feature of our universe, one that connects the technology in our pockets to the most extreme objects in the cosmos, and hints that our personal experience of time's steady flow is just a local and very relative phenomenon. But if the strange warping of time around massive objects like neutron stars shows us how gravity can stretch and slow our personal experience of time, the concept of the multiverse takes this relativity to a truly cosmic scale, suggesting that time might not even exist in countless other universes. The idea that our cosmos is just one bubble in a vast, frothing ocean of universes, each with its own unique set of physical laws, is one of the most breathtaking and humbling in all of modern cosmology. And within this infinite tapestry of realities, some of those universes could be fundamentally, utterly timeless realms where the concept of a flowing now is completely absent, and existence is not a dynamic process but a single, frozen, eternal state. This mind-expanding vision is championed by physicists like Max Tegmark, who categorizes different levels of the multiverse. In what he calls the level Roman 4 multiverse, the very constants of nature and the laws of physics themselves can vary from one universe to the next. In such a grand ensemble, it becomes not just possible but statistically inevitable that there are universes where the parameters that give rise to time as we know it simply do not apply. In these exotic branches of reality, the dimension of time might be curled up, absent, or fundamentally static. The entire history of such a universe, from its hypothetical beginning to its end, wouldn't unfold like a movie. It would exist all at once, like a completed sculpture or a finished book sitting on a shelf. Every event, every star, every potential life form would be locked into a single, unchanging configuration, a frozen moment stretched across the entirety of existence. This immediately plunges us into a deep and unsettling philosophical paradox about identity and consciousness. Let's say, in this vast multiverse, there is a static, timeless universe that contains a configuration of matter identical to your body and brain at this very moment. In that frozen realm, there is a version of you, but it is motionless, unchanging, and unaware. It has no past to remember and no future to anticipate. The question then becomes, is that frozen statue truly you? Does it possess consciousness, or is consciousness an inherently dynamic process that requires the flow of time? Our entire sense of self is built upon memory of the past and anticipation of the future. If those are removed, what remains? It challenges the very core of what we believe it means to exist, suggesting that our continuous stream of awareness might be an illusion contingent upon a very specific, time-bound set of physical laws that are not universal. These ideas are not just wild speculation, they are grounded in serious scientific frameworks. The theory of eternal inflation, for instance, suggests that the rapid expansion of space that fueled our Big Bang is not a unique event but is ongoing in a wider, background multiverse. New pocket universes are constantly bubbling into existence, each with a random, unpredictable set of physical constants. Some of these newborn universes might have laws that allow for a rich, flowing time like ours, while others might be stillborn or exist as timeless, static structures. Furthermore, the famous many worlds interpretation of quantum mechanics proposes that every time a quantum event has multiple possible outcomes, the universe literally branches into multiple copies, each containing one of those outcomes. While these branches are usually thought of as dynamic, it's conceivable that some of these branching pathways could lead to timelines or universes where the arrow of time is undefined or non-existent. For us, sitting here in our time-bound reality, this is a thrilling and vertigo-inducing thought. It means that alternative versions of reality are not just science fiction, they could be a fundamental part of the architecture of existence, existing right alongside our own in a higher dimensional space. Some of those realities could be so alien that the very concept of change is meaningless, operating on principles entirely outside of time. This doesn't just expand our concept of what's possible, it shatters it, suggesting that our experience of a linear, flowing time is not the default state of the cosmos, but merely a local, and perhaps even rare, condition within an infinitely varied multiverse. Yet, even as we grapple with the idea that time might be an emergent property encoded on a distant surface, another profound concept in theoretical physics offers a radically different perspective on timelessness, one that suggests our entire universe might be a kind of cosmic projection. This is the holographic principle, a daring idea that proposes all the information contained within any given volume of space, every star, every planet, every event happening within it, can be completely described by data encoded on its two-dimensional boundary. Think of it like a futuristic hologram where a three-dimensional image is projected from a flat, two-dimensional surface. In this astonishing framework, the dimension of time itself might not be fundamental to the interior of this space, but could instead emerge from complex interactions and correlations happening on that lower dimensional boundary. This leads to the incredible possibility that the interior of such a region, like the heart of a black hole, could be fundamentally timeless, a place where our familiar experience of temporal flow is nothing more than a compelling illusion. The origins of this principle are deeply tied to one of the most persistent puzzles in modern physics, the black hole information paradox. When matter falls into a black hole, it seemingly vanishes, taking all information about its properties with it. This violates a core tenet of quantum mechanics, which states that information can never be truly destroyed. Theorists like Leonard Susskind wrestled with this for decades. Their groundbreaking work suggested a stunning resolution. The information isn't lost inside the black hole at all. Instead, it is meticulously encoded on the black hole's event horizon, its two-dimensional boundary, in unimaginably tiny pixels at the scale of a Planck length. The event horizon acts like a cosmic hard drive, storing a perfect record of everything that ever fell in. What we perceive as the three-dimensional interior, with its passage of time and its terrifying singularity, might be a projection from this data-rich surface. In this view, falling into a black hole wouldn't be a journey through time and space in the conventional sense. It would be more like entering a fully immersive virtual reality, one generated by the information on the horizon's surface. This creates a breathtaking paradox that completely inverts our intuition. Imagine you are an astronaut plunging into a black hole. From your perspective, you continue to experience time normally as you cross the event horizon and are pulled toward the central singularity. Your watch keeps ticking, your heart keeps beating, and you experience a sequence of events. but from the perspective of an outside observer watching you fall, you never actually cross the horizon. Your image appears to freeze there, smeared across the surface, with your information becoming a permanent part of the horizon's data structure. So which experience is real? The holographic principle suggests that both are valid in their own reference frames, but the more fundamental description of reality is the one on the boundary. Your vivid, personal experience of time inside the black hole is a projected illusion, much like the convincing depth of a hologram that has no true depth at all. The true, timeless reality is the frozen, encoded information on the surface. The implications of this ripple out far beyond black holes, potentially describing the entire universe. Some versions of string theory and quantum gravity suggest that our three-dimensional universe of space and time, with all its galaxies and history, could itself be a holographic projection from a two-dimensional surface at the cosmic horizon. If this is true, then time itself is not a fundamental feature of reality, but an emergent property that arises from the way information is processed and related on this vast cosmic boundary. This blends the worlds of information theory and gravity in a completely new way, suggesting that the universe is at its heart computational and that the flow of time is a derived phenomenon, not a primary ingredient. It's a concept that challenges the very core of our experience, proposing that the stage upon which we live our lives is, in a sense, the grandest illusion of all. Just as the holographic principle redefines time as an emergent illusion, another cosmological model offers a dramatic alternative to the idea of a single, linear timeline with a definitive beginning and end. This is the concept of the cyclic universe, a grand vision where the cosmos undergoes an endless, rhythmic dance of birth, death, and rebirth. In this model, our Big Bang was not the absolute start of everything, but merely the most recent chapter in an infinite series of expansions and contractions. Each cycle begins with a fiery explosion from a singularity and ends in a catastrophic collapse back into one, a moment often called the Big Crunch. And it is in these pivotal moments of transition, the bounce from crunch to bang, that time itself may undergo a radical reset, dissolving into a state of timelessness before a new arrow of time emerges for the next cosmic cycle. This breathtaking idea finds a powerful and unexpected echo not in a modern physics lab, but in the 19th century writings of the German philosopher Friedrich Nietzsche. He grappled with the concept of eternal return or eternal recurrence, which he presented as a profound thought experiment. He asked, what if every event in your life, every joy and every pain, were destined to repeat itself in exactly the same way, over and over again for all eternity? For Nietzsche, this wasn't necessarily a literal cosmological theory, but a psychological test of one's attitude toward life. To embrace this idea was to affirm existence completely, to love one's fate so entirely that you would willingly relive it forever. While Nietzsche's was a philosophical proposition, its thematic resonance with the scientific model of a cyclic universe is striking. Both visions shatter the linear, progressive view of history, replacing it with a grand, circular rhythm where endings are also beginnings. The mechanics of a cyclic model present a fascinating paradox for the nature of time. During the universe's expansion phase, time has a clear direction, defined by the increase of entropy and the unfolding of structure. As the universe reaches its maximum size and begins to contract under its own gravity, this arrow of time could, in theory, continue pointing forward. But many theorists suggest that at the moment of the Big Crunch, as all matter and energy are compressed into an ultra-hot, ultra-dense state, the laws of physics as we know them would break down. In that singularity, the concepts of before and after would cease to have any meaning. Time would become undefined. the subsequent bounce and a new Big Bang would not be a continuation of the old timeline, but the genesis of an entirely new one, with its own new arrow of time emerging from the timeless chaos of the singularity. This means the history of our universe, all of our galaxies, stars, planets, and lives, is not a unique story but one of countless iterations, each separated from the next by an interval of pure, unfathomable timelessness. This view fundamentally redefines our understanding of eternity. We often imagine eternity as an infinite line stretching forward into the future, but in a cyclic cosmos, eternity is a circle. There is no ultimate beginning and no final end. There is only the endless, repeating cycle of creation and dissolution. This challenges the very foundation of linear time, suggesting that the one-way direction we experience is not a universal constant, but merely a phase within a much larger cyclical process. The timeless intervals between cycles act as cosmic resets, erasing the slate and allowing for a new universe with potentially slightly different physical constants to be born anew. Our existence, then, is not a single, fleeting moment in a linear history, but a recurring verse in an eternal cosmic poem, each recitation separated from the next by a silent, timeless caesura. The implications are as humbling as they are awe-inspiring. It suggests that every event, from the formation of the first hydrogen atom to the rise of human civilization, has potentially happened an infinite number of times in the past and will happen an infinite number of times in the future. This doesn't necessarily mean every cycle is identical. Some models incorporate subtle changes with each iteration, but the core idea remains: our universe's story is not unique. This cyclic view offers an elegant alternative to the puzzle of the initial singularity, replacing the daunting question of what happened before the Big Bang with what happened before the previous cycle. While this might seem to simply push the problem back a step, it reframes the origin of the cosmos from a singular, miraculous event into a perpetual, natural process, a heartbeat of existence whose rhythm pulses across an infinite, timeless expanse. But just as we begin to wrap our minds around the idea that particles can be linked in a way that defies time and space, we encounter a paradox that strikes at the very heart of what it means to observe the universe. This brings us to the strange and central role of the observer in quantum mechanics. In our everyday world, we assume that objects exist with definite properties whether we're looking at them or not. A tree falling in a forest makes a sound, as the old thought experiment goes, even if no one is around to hear it. But in the bizarre realm of the quantum, this common-sense notion completely falls apart. The act of measurement, the simple fact of observation, seems to play an active and crucial role in determining reality itself. This idea is central to the famous Copenhagen interpretation of quantum mechanics, pioneered by figures like Niels Bohr and Werner Heisenberg. Before a quantum system like an electron or a photon is measured, it doesn't possess a definite property, such as a specific position or a specific spin. Instead, it exists in a blurry cloud of potentiality, a superposition of all possible states at once. It's only at the precise moment when an observation is made that this probability wave, as it's called, collapses into a single, definite outcome. In this view, the observer is not a passive recorder of a pre-existing reality, but an active participant in its creation. The tree in the quantum forest only acquires a definite position and makes a specific sound the moment someone is there to observe it. This places consciousness, or at the very least the physical process of measurement, in a profoundly powerful and puzzling position. This leads to a deeply unsettling question about the nature of time in a universe without observers. If the definite flow of events only emerges through the act of observation, What happens in regions of the cosmos where there are no conscious beings to make a measurement? Imagine a distant galaxy, isolated and alone, with no planets, no life, and no one to ever look upon it. According to this interpretation, without an observer, the entire galaxy might remain in an indefinite, fuzzy state of potentiality. Its stars would not shine in a definite way. Its history would not unfold in a clear sequence of cause and effect. It would exist in a kind of suspended animation, a timeless haze of possibilities, waiting for a conscious glance to bring it into sharp focus. This suggests that time, as a linear progression of definite events, might not be a fundamental feature of the cosmos, but a phenomenon that emerges from the interaction between the quantum world and the act of observation. This paradox forces us to confront the boundaries between physics and philosophy, between the objective and the subjective. Is the universe truly a mind-independent reality, or is our consciousness somehow woven into its very fabric? Most physicists today favor interpretations that avoid making consciousness a primary force, suggesting instead that the observer can be any macroscopic measuring device that causes decoherence, the process that makes quantum probabilities appear classical. But even in these models, the act of measurement remains a pivotal event that defines reality. It hints that our experience of a smooth, flowing time with a clear past and future is the result of countless such measurements happening constantly all around us, collapsing quantum possibilities into a classical, coherent history. The role of the observer, therefore, is not just to see the universe, but to help crystallize it from a realm of timeless potential into the definite, temporal world we call home. This profound connection between observation and reality leads us directly to one of the most controversial and mind-bending paradoxes of all: the idea that time itself might not be a fundamental feature of the cosmos, but rather a phenomenon that emerges from the simple act of looking at something. In the strange world of quantum mechanics, the properties of a particle, its position, its momentum, even its very existence, are not fixed until the moment it is measured. Before that critical instant, the particle exists in a ghostly state of pure potential, a blur of all possibilities known as a superposition. In this fuzzy, unobserved state, the clean, linear progression of time we take for granted may also become blurred and undefined, suggesting that our experience of a flowing now is inextricably linked to the process of observation itself. This radical view is at the heart of the Copenhagen interpretation, the traditional framework for understanding quantum mechanics championed by pioneers like Niels Bohr and Werner Heisenberg. They proposed that the wave function, the mathematical description of a quantum system's probabilities, doesn't just describe a particle. It is the particle's reality until an observation forces it to collapse into a single, definite state. In this moment of collapse, a specific outcome is chosen from the haze of possibilities, and a definite event is added to the timeline of the universe. It's as if each observation is a stitch in the fabric of time, pulling a single thread from a tangled skein of potentialities and weaving it into the solid tapestry of history. From this perspective, time isn't a pre-existing river that carries events along. It's a sequence that is built moment by moment through an endless series of quantum measurements. This immediately plunges us into a deep philosophical abyss. If the definite flow of time requires an observer, what happens in the unimaginable vastness of empty space, in the voids between galaxies where no conscious being has ever looked? Consider a lone electron drifting in the deep void for billions of years, far from any instrument or life form. According to this interpretation, without a measurement to collapse its wave function, it might not have a definite position or spin. It exists in a state of suspended animation, a timeless limbo where all possible histories remain open and unrealized. Now scale that up. Could entire star systems, adrift in the cosmic dark, be trapped in a similar state of quantum ambiguity? It's a staggering thought that challenges the very notion of an objective, observer-independent reality, suggesting that the universe without someone to see it might not be a universe of definite events at all, but a static, timeless potentiality waiting to be realized. This paradox doesn't just blur the line between physics and philosophy, it erases it entirely, forcing us to ask what we even mean by existence. Does a tree falling in a forest with no one around truly make a sound, or does it merely create a potential for sound that goes unrealized? The quantum version of this question is far more profound. It asks if the universe had a history before the first conscious observers emerged to measure it. Perhaps the Big Bang itself remained a superposition of possibilities until the first ancient star formed, and in some minimal quantum sense, observed its surroundings, beginning the long process of collapsing the wave function of the entire cosmos. This isn't to say that human consciousness magically creates reality, but that the physical process of measurement, which can be performed by any interacting system, not just a person, is the engine that drives the emergence of time from a sea of timeless potential. Our experience of a flowing, linear time may be the ultimate collective illusion, a story we tell ourselves about a universe that is, at its most fundamental level, a timeless and ever-changing dance of probability. But just as we begin to accept that our experience of time might be a construct of observation, we are forced to consider an even more radical possibility, that the very stage upon which reality plays out has more dimensions than we can perceive, and within those hidden folds, time itself may not even exist. This brings us to the world of string theory, a breathtakingly ambitious framework that attempts to weave together the laws of gravity and quantum mechanics by proposing that the fundamental building blocks of the universe are not point-like particles, but unimaginably tiny, vibrating strings. To make the mathematics of this theory work, these strings must vibrate in a universe that has not just the 4 dimensions we experience, 3 of space and 1 of time, but a total of 10 or even 11 dimensions. The reason we don't see these extra dimensions is that they are compactified or curled up into an infinitesimally small size, far beyond the reach of our most powerful microscopes. Think of it this way: imagine a long, stretched-out garden hose. From a great distance, it looks like a simple one-dimensional line. But if an ant were to crawl onto that hose, it would discover an entire second dimension, the circular path around the hose's circumference. The extra dimensions of string theory are like that circular path, but curled up into a space billions of times smaller than an atom. Theorists like Brian Greene have spent their careers exploring the profound implications of this idea, and one of the most startling is what it might mean for the nature of time. In these hyper-compactified dimensions, the very concept of temporal flow could be completely different. They might be so tightly wound and static that the strings vibrating within them experience no change whatsoever, creating microscopic pockets of perfect, eternal stillness right under our noses, woven into the fabric of everything we see and touch. This isn't just a mathematical curiosity. It could have real, observable effects on the forces and particles that make up our world. The specific way these extra dimensions are folded and twisted, their shape and topology determines how the fundamental strings vibrate. And the vibration patterns of these strings are what we perceive as the different properties of particles, their mass, their charge, and even the forces they feel. If time behaves differently or is frozen solid within these compactified dimensions, it could directly influence the properties of our 4-dimensional reality. For instance, the strength of gravity or the mass of an electron might be set by the timeless, geometric structure of these hidden realms. It's a staggering concept. The constants of nature that make our universe suitable for life could be frozen into place by the architecture of dimensions where time itself does not flow. This paradox fundamentally expands our understanding of where timelessness might be found. It's not just in the distant hearts of black holes or the far future of heat death. It could be here, everywhere, woven into the microscopic foundation of reality itself. Our smooth, flowing experience of time in the four large dimensions we inhabit might be just the surface level of a far deeper and more complex reality. A reality that includes timeless, frozen dimensions which anchor the very laws of physics. This suggests that time is not a universal constant but a local and emergent property, a phenomenon that only exists in the dimensions large enough to support its flow, while the rest of existence remains locked in a state of permanent, silent stasis. And if the idea of hidden, timeless dimensions challenges our perception of reality, the next paradox introduces a form of matter that seems to defy the most fundamental laws of physics altogether. This is the concept of time crystals, a bizarre new phase of matter that exhibits motion and order in its ground state, the state of lowest energy, without ever consuming any energy or winding down. Proposed by Nobel laureate Frank Wilczek, this idea was initially met with skepticism because it seemed to suggest the possibility of perpetual motion, a concept long thought to be impossible under the laws of thermodynamics. But through ingenious experiments, scientists have now created these crystals in labs using systems like chains of ions or defects in diamonds, confirming that they are not only possible but a genuine new state of matter. So how do they work? A normal crystal, like a diamond, has atoms arranged in a repeating pattern in space. A time crystal has a structure that repeats not in space, but in time. It oscillates between two or more configurations with a fixed, regular period, like a clock that ticks forever. The astonishing part is that this ticking continues indefinitely even in the system's ground state, the quantum equivalent of being completely at rest and devoid of usable energy. It's not that the time crystal creates energy from nothing. Rather, it establishes a stable, periodic rhythm that is immune to energy loss, a kind of quantum dance that never requires a fresh input of power to keep going. This breaks what's known as time translation symmetry, the idea that the laws of physics are the same at every moment in time, because the time crystal picks out a specific rhythm, a privileged tick-tock, as part of its fundamental existence. This creates a profound paradox that sits at the intersection of timelessness and perpetual change. In an environment that is otherwise static and featureless, the ground state, the time crystal maintains a dynamic, ordered pattern that repeats with perfect regularity. It's a system that has change without a cause, rhythm without energy consumption, and motion within a state of ultimate stillness. For instance, if you could place a time crystal into the theoretical heat death of the universe, where all other change has ceased and time has lost all meaning, this strange object would continue its endless, silent ticking, a lone metronome keeping time in a timeless void. It's a breathtaking demonstration that even in the absence of energy gradients and the arrow of time, the quantum world can still host a form of dynamic order, forever oscillating in a dance that has neither a beginning nor an end. Yet, even as we explore the abstract landscapes of hidden dimensions and quantum foam, one of the most astonishing discoveries in modern physics brings the paradox of timeless motion into our very own laboratories. This is the world of time crystals, a bizarre and groundbreaking new phase of matter that seems to achieve the impossible, perpetual, clock-like motion without any input of energy. To understand just how radical this idea is, we need to remember a fundamental law of the universe, the second law of thermodynamics. It tells us that everything tends toward disorder, that all systems eventually wind down and reach equilibrium, a state of maximum entropy where all useful energy has been dissipated and all motion ceases. A pendulum will eventually stop swinging. A bouncing ball will come to rest. The idea of anything moving forever without an energy source has long been considered a fantasy, a violation of the most basic principles of physics. But time crystals don't just challenge this rule, they dance around it using the bizarre loopholes of quantum mechanics. The concept was first proposed by Frank Wilczek, a Nobel Prize-winning physicist, who asked a deceptively simple question: could there be a form of matter that is to time what a normal crystal is to space? A regular crystal, like a diamond or a snowflake, has atoms arranged in a repeating, periodic pattern in space. It breaks what physicists call spatial translation symmetry because it picks out specific points in space for its atoms to occupy, rather than being uniform everywhere. Wilczek wondered if a similar thing could happen in time. Could there be a system that naturally settles into a state with a repeating, periodic pattern in time? In other words, could it oscillate between different configurations forever, even in its ground state, its lowest possible energy state, where no further energy can be extracted and no motion should be possible? The initial reaction from many in the physics community was deep skepticism, as it sounded suspiciously like the classical impossible dream of a perpetual motion machine. But then, through ingenious experiments, researchers did the seemingly impossible. They created time crystals in the lab. They didn't use magic or defy thermodynamics. They harnessed the unique properties of the quantum world. In one pioneering experiment, scientists used a chain of ytterbium atoms or a specific set of defects in a diamond, known as nitrogen vacancy centers. They prepared this system in a special quantum state and then gave it a single initial kick with a laser pulse. According to classical physics, the system should eventually relax and stop moving. But in these experiments, something remarkable happened. The system started oscillating between two states at a very specific frequency, and it kept doing so indefinitely. This oscillation wasn't driven by the continued application of the laser. The laser was only used to start the process. The time crystal had found a rhythm and was locked into it, ticking away like a perfect clock that never needs winding, all while remaining in its quantum ground state. This creates a breathtaking paradox that stands at the intersection of timelessness and change. A time crystal exists in a state of perfect periodic order in time, yet it does so without consuming any energy. It's a system that has dynamic motion while being, in a very real sense, frozen in its lowest energy configuration. It breaks what physicists call time translation symmetry. In an empty, featureless universe, the laws of physics are the same at every moment. No one instant in time is any different from another. But a time crystal picks out a specific rhythm, making a particular frequency of oscillation special. It's as if the crystal creates its own personal, privileged sense of time from a state that should be utterly still and timeless. Imagine a single metronome, ticking back and forth with perfect regularity, placed in the theoretical heat-death of the universe where all other change has ceased and time has lost all meaning. While everything else is frozen in a state of maximum entropy, this one object would continue its endless, silent oscillation, a beacon of dynamic order in a sea of static equilibrium. The implications of this are profound, not for building actual perpetual motion machines. They can't do useful work or create energy, but for our fundamental understanding of matter and time itself. Time crystals show us that even in a state of ultimate stillness, the quantum world can host a form of fragile, protected motion. They are a stunning example of how timelessness and dynamic behavior are not always mutually exclusive. This cutting-edge research opens up new possibilities for quantum computing, where such stable, protected states could be used to create incredibly robust quantum memory. resistant to the environmental noise that typically destroys quantum information. More philosophically, the time crystal is a powerful reminder that the universe still holds deep surprises, challenging our most cherished assumptions and revealing that even in the deepest stillness, a subtle, eternal dance may still be going on. Yet even as we marvel at the laboratory creation of time crystals, we find that the human mind itself has long been capable of accessing its own profound states of timelessness, not through complex equipment, but through the inward journey of contemplation and meditation. Across countless spiritual traditions and mystical paths, from the deep samadhi of Buddhist monks to the ecstatic visions of Christian mystics, individuals have reported experiencing a state of consciousness where the familiar flow of time completely dissolves, replaced by a profound sense of unity with all that is, and an overwhelming feeling of being immersed in an eternal, unchanging present. This is not merely a poetic metaphor. It is a consistent, repeatable, and deeply transformative subjective experience that points toward a fundamental capacity within the human brain to transcend its own ordinary perception of temporal flow. The 14th century Christian mystic Meister Eckhart gave this experience a powerful name, the eternal now. For Eckhart, this was not an abstract concept but a lived reality, a state of grace where the soul touches the divine and perceives existence from a vantage point outside of sequential time. In this state, the anxious chatter of the mind rehashing the past and worrying about the future falls completely silent. What remains is a vast, spacious awareness that simply is, a pure witnessing of the present moment so total and complete that it feels unbounded by time. Similar descriptions echo through the ages and across cultures. Hindu rishis speaking of merging with the timeless Brahman, Sufi poets describing the annihilation of the self in the eternal beloved, and Zen masters pointing directly to a timeless awareness that is our true nature before a single thought arises. These are not descriptions of a passive trance, but of a hyper-aware, lucid state of being where the illusion of separation vanishes. What is truly astonishing is that modern neuroscience is now beginning to map the changes in brain activity that correlate with these profound subjective reports. Using functional MRI and EEG scans on experienced meditators, scientists have observed a notable quieting of the default mode network, a web of brain regions that is highly active during self-referential thinking, mind-wandering, and the constant mental time travel that defines our usual sense of self. When this network downshifts, the constant narrative of me and my story recedes. Simultaneously, there often is an increase in synchronized, slower brain waves like theta and delta, which are associated with deep relaxation, heightened intuition, and a loss of the usual boundaries between self and world. This neurological shift appears to be the biological underpinning of the feeling of timeless unity, suggesting that the mystical eternal now has a real, measurable footprint in the physical brain. This creates a beautiful and deeply personal paradox that bridges the vast gap between the outer cosmos and our inner world. For centuries, the experience of timelessness was the exclusive domain of saints and mystics, often framed in purely spiritual or philosophical terms. Meanwhile, physicists were discovering timelessness as a mathematical property of singularities and quantum fields. Now, these two great rivers of inquiry are converging. The timeless void inside a black hole and the timeless unity experienced by a meditator may be descriptions of the same fundamental reality, approached from two completely different directions, one through the external telescope and equations, the other through the internal microscope of disciplined consciousness. Both paths lead to the same stunning conclusion, that the flowing, linear time we take for granted is not the whole story, and that a state of timelessness is not an abstract theory but a potential experience accessible to human awareness. This insight is perhaps the most empowering of all our explorations. It means that you don't need a spacecraft to visit a timeless region. The portal might be as close as your next breath. The peace and insight that mystics describe the liberation from the tyranny of past regret and future anxiety is not reserved for a select few, but is a latent capacity within us all. It suggests that by exploring the depths of our own consciousness through practices like meditation, we can personally verify what physics can only describe mathematically, that at the heart of reality lies a profound, silent, and timeless unity. This doesn't diminish the wonder of cosmic paradoxes, but instead completes the picture, revealing that the universe's greatest mysteries are not only out there in distant space, but also in here, waiting to be discovered in the quiet spaces of our own mind. But what if the very tool we use to understand the cosmos, mathematics, could offer us a key to smooth away these infinite, jagged edges and reveal a universe that is, in a profound sense, complete and whole? This is the brilliant and mind-bending innovation of Stephen Hawking's concept of imaginary time. To navigate around the troublesome infinities of the Big Bang singularity, Hawking and his collaborator James Hartle proposed a daring mathematical pivot: treat the dimension of time not as a real number on a line, but as an imaginary number, a concept denoted by the letter I, which is defined as the square root of -1. While this might sound like an abstract trick with no connection to reality, its implications are nothing short of revolutionary, transforming the universe's history from a story with a definitive beginning into a perfectly smooth, self-contained geometric object where the very idea of a starting point becomes meaningless. In this extraordinary framework, imaginary time behaves not like the time we experience, but like a fourth spatial dimension. Imagine the difference between a straight line and a circle. Our ordinary, real time is like that line. It has a starting point, the Big Bang, and presumably an end point. But in imaginary time, the history of the universe is more like the surface of a sphere, such as the Earth. You can walk in any direction on Earth forever without ever falling off an edge or finding a true beginning. The North Pole isn't a point of creation. It's just another point on the globe, no different in nature from any other. In the Hartle-Hawking no-boundary proposal, the universe in imaginary time is exactly this: finite in extent, yet having no boundary, no edge, no singularity where the laws of physics break down. The Big Bang ceases to be a violent explosion from nothing and becomes more like the North Pole of this cosmic sphere, a point we can identify mathematically, but one that is just a part of the smooth, continuous, and complete geometry of spacetime. This elegant model resolves the thorny issue of the initial singularity by simply eliminating it. There is no longer a point of infinite density because there is no boundary to spacetime that requires a prior cause. The question, what happened before the Big Bang, becomes as nonsensical as asking, what is north of the North Pole? In the imaginary time realm, there is no before, because there is no time as we know it in which a before could exist. The universe just is in a timeless, unchanging geometric state. This doesn't mean our experience of real time is an illusion. Rather, it suggests that our flowing, linear time is a kind of emergent, approximate description that arises from this deeper, timeless reality once the universe becomes large enough and cool enough. The singular beginning is smoothed over, replaced by a graceful, curved geometry that needs no creator or external trigger to exist. The power of this paradox lies in its demonstration of how mathematics can radically redefine our concept of reality. By accepting the seemingly fanciful idea of imaginary numbers as a valid descriptor for time, Hawking provided a stunningly elegant solution to one of cosmology's biggest puzzles. It offers a vision of a self-contained universe, a cosmos that requires no external ignition or mysterious first cause because it has no boundary condition that needs explaining. It is a universe that emerges from pure geometry, a timeless, seamless whole where the distinction between past, present, and future is a local phenomenon, not a fundamental truth. This abstract but profoundly powerful idea shows that the keys to understanding the deepest mysteries of existence might not be found in bigger telescopes, but in the uncharted territories of mathematical imagination, revealing a reality where timelessness is not a paradox but the very foundation of all that is. Yet as we contemplate the profound stillness of heat-death, we must turn our attention to the mysterious force that is actively shaping this very destiny, a force that is not pulling the universe together, but relentlessly driving it apart. This is the enigma of dark energy, an invisible pressure permeating the vacuum of space itself, causing the expansion of the cosmos to not just continue, but to accelerate at an ever-increasing rate. Discovered in the late 1990s through observations of distant supernova, this finding was so shocking it earned a Nobel Prize, fundamentally rewriting the story of our universe's fate. Rather than a gradual slowdown from the initial momentum of the Big Bang, we live in a cosmos that is flying apart faster and faster with each passing moment, a runaway expansion powered by this unknown, repulsive energy that makes up about 70% of the entire universe. This accelerating expansion paints a startlingly bleak picture of the far future, a scenario cosmologists call the Big Rip. If dark energy's repulsive force continues to strengthen over time, it won't just push galaxies away from each other. It will eventually overcome every binding force in nature. First, the gravitational glue holding clusters of galaxies together will be defeated, sending individual galaxies flying off into their own isolated trajectories. Then, the powerful forces holding individual galaxies together will be overcome, tearing stars away from each other. As the acceleration becomes unimaginably violent, even individual solar systems will be ripped apart, followed by planets being torn from their stars. In the final, terrifying moments, the very fabric of spacetime itself could be shredded, with the repulsive force overwhelming the forces that hold atoms together, and then the nuclei within those atoms, dissolving all matter into a mist of disconnected elementary particles spread infinitely thin across a vast, cold, and empty void. Within this apocalyptic vision lies a profound temporal paradox. As the universe expands and accelerates, the distance between any 2 points grows at an ever faster rate. There is a critical point in this expansion where two objects can become so far apart that the space between them is expanding faster than the speed of light. This doesn't violate relativity because it is space itself that is stretching. No information or matter is moving through space faster than light. The consequence, however, is absolute. Once two regions of space are separated in this way, they become causally disconnected. No signal, no particle, no influence of any kind can ever travel between them again. They are forever shut off from one another, each existing in its own isolated pocket of reality. In such a state, the concept of a shared cosmic time breaks down completely. There is no universal now because there is no way to synchronize clocks or events between these isolated regions. Time, which relies on causality and the sequence of events, loses its meaning on the largest scales, fracturing into countless disconnected, local timelines that can never interact or influence each other again. Cosmologists like Lawrence Krauss have explored the implications of this vacuum-dominated future. As dark energy drives the acceleration, the universe becomes increasingly empty and barren. All structures, galaxies, stars, planets will eventually dissipate and vanish over trillions of years. With no structures left to form and no energy gradients to drive any processes, the universe approaches a state of perfect uniformity, a near equilibrium where absolutely nothing happens. In this state of maximum entropy, the arrow of time, which is defined by the increase of disorder, effectively vanishes because disorder can no longer increase. It has reached its maximum possible value. Without change, there can be no flow of time. The cosmos becomes a static, eternal, and timeless void. Dark energy, therefore, is not just a curious component of the universe's energy budget. It is the ultimate agent of timelessness, actively engineering a future where time itself becomes a forgotten relic, an emergent property that fades away as the universe achieves a final, silent, and eternal equilibrium. But if the idea of a universe tearing itself apart feels almost too vast to comprehend, the next paradox brings our focus back to one of the most stubborn and fundamental puzzles in all of physics, a conflict so deep that it pits our two most successful theories against each other in a battle over the soul of reality itself. This is the black hole information paradox, and it forces us to ask a deceptively simple question with universe-shattering implications. When something falls into a black hole, is all information about it truly and irrevocably lost? At first glance, the answer seems obvious. General relativity tells us that anything crossing the event horizon is inexorably pulled toward the central singularity, a point where the laws of physics break down and time itself ceases to exist. From this perspective, every detail about the fallen object, whether it was a star, a book, or a person, its composition, its shape, its history is utterly obliterated, scrubbed from the universe forever. It's as if reality itself has a one-way trash can with no recovery option. But quantum mechanics, the wildly successful rules governing the atomic and subatomic world, paints a completely different picture. One of the most sacred principles in quantum theory is the conservation of information. This isn't about conserving data like a computer file. It's a far deeper statement about the universe's fundamental reversibility. In principle, if you could know the exact quantum state of every particle in the universe at this very moment, you could use the laws of physics to rewind the tape, perfectly reconstructing every prior state of the universe all the way back to the Big Bang. Information, in this sense, is never destroyed. It merely changes form. It might get scrambled into an unimaginably complex mess, like an egg being mixed into a cake batter. But in theory, the recipe is always preserved. If you could reverse all the interactions, you could unmix the batter and get the egg back. The black hole singularity, by seemingly deleting information permanently, doesn't just hide things. It burns the recipe book, violating a cornerstone of quantum theory and creating a catastrophic contradiction between our two best descriptions of nature. For decades, Stephen Hawking was a leading proponent of the idea that information was indeed lost in black holes. His own discovery of Hawking radiation seemed to support this. This radiation, which causes black holes to slowly evaporate over eons, was predicted to be completely random and thermal, carrying no information whatsoever about what had fallen in. It would be like a fire that burns a priceless, unique library of books into nothing but a featureless pile of identical hot ashes. The information about each individual book would be gone forever. Hawking's stance meant that physicists would have to choose. Either general relativity was wrong about the nature of the singularity, or quantum mechanics was wrong about the conservation of information. This was an appalling choice for any physicist, as both theories have been spectacularly verified by experiment. The search for a resolution to this paradox has spawned some of the most creative and mind-bending ideas in modern theoretical physics. One of the most prominent is the holographic principle, which we touched on earlier. It suggests a brilliant way out. The information isn't actually lost inside the black hole because it was never truly there to begin with. Instead, it is perfectly and meticulously encoded on the event horizon itself, the two-dimensional boundary of the black hole. Imagine the event horizon as a cosmic movie screen. A three-dimensional movie is playing inside the black hole the story of the collapsing star and anything else that fell in. But the information for that entire three-dimensional movie is stored on the two-dimensional surface of the screen. An observer falling in would experience the full, immersive 3D movie, complete with the flow of time. But for an outside observer, the entire history of the black hole's interior is just a frozen, timeless image painted on the surface. This resolves the paradox by stating that information is never destroyed. It is just transferred from the volatile, time-bound interior to the stable, timeless boundary, where it is preserved forever, even as the black hole itself evaporates away via Hawking radiation. Another, more radical solution is the infamous firewall paradox. If information is to be preserved and carried out by Hawking radiation, then the event horizon cannot be the smooth, gentle entryway that general relativity describes. Instead, it must be a blazing wall of unimaginably high energy particles, a literal firewall that would instantly incinerate anything attempting to cross it. This idea emerges from the complex quantum entanglement between particles just inside and just outside the horizon. To preserve the information and make the physics consistent on the outside, the entanglement must break down at the horizon itself, releasing a tremendous amount of energy. This solution saves the conservation of information but at a terrible cost. It destroys the principle of equivalence, a foundational idea in general relativity that says free falling through an event horizon should be an unremarkable local experience. You can't have both a smooth passage into a black hole and perfect information conservation. You might have to choose between them. This intense, ongoing debate is far more than an academic squabble. It is a fundamental probe into the nature of reality, forcing us to ask what happens when time itself becomes irrelevant. The solutions, whether holography or firewalls or something else entirely, all point toward a staggering conclusion. Our intuitive understanding of time and information is profoundly incomplete. The timeless region inside a black hole is not just a weird anomaly. It is a crucible where the deepest laws of the universe are tested and forged, revealing that information might be the most fundamental currency of reality, and that time itself could be a secondary, emergent property that arises from the way that information is processed and stored across the cosmos. But what if the very fabric of our reality, including the relentless flow of time, is not a fundamental feature of the cosmos but a sophisticated construct, an illusion rendered by lines of code in a universe-scale simulation? This is the provocative premise of the simulation hypothesis, an idea championed by philosophers like Nick Bostrom that pushes the paradox of timelessness into the realm of metaphysics and computer science. Bostrom's argument isn't mere science fiction, it's a serious statistical proposition. If it is possible for a sufficiently advanced civilization to create conscious, detailed simulations of reality, and if such civilizations are likely to run vast numbers of these simulations for research or entertainment, then the number of simulated minds could vastly outnumber the number of base reality, biological minds. Statistically speaking, we are more likely to be one of those simulated beings than an organic one in the original universe. This isn't a claim that we are in a simulation, but a compelling argument that we cannot dismiss the possibility. Within this framework, the nature of time becomes completely malleable. In a simulation, time isn't a fundamental river flowing from past to future. It is a variable, a parameter controlled by the simulation's clock speed. The simulator could, in principle, pause the entire program. In that paused state, every process, every particle interaction, every conscious thought would be frozen in a single, timeless instant, stored as data in the memory of some unfathomable computer. There would be no change, no progression, just a static snapshot of all existence. The simulator could then rewind the simulation, replaying events backward or fast forward to a future state. It could create backup saves of the universe at a specific date and restart from that point, creating branching timelines. In such a reality, the cosmic timelessness we've explored inside black holes or at the heat death of the universe wouldn't be mysterious physical anomalies. They would be akin to the program being paused or stopped, a feature of the underlying computational architecture rather than a law of physics. This perspective invites us to view the most baffling aspects of quantum mechanics in a startling new light. The strange phenomenon where particles don't have definite properties until they are measured, the core of the quantum measurement problem, could be explained by a simple optimization technique. In a vast simulation, rendering every detail of every particle in the universe in full fidelity would require unimaginable processing power. It would be far more computationally efficient to only render the details of a quantum system at the moment it is observed, much like a video game only loads the graphics for the part of the world the player is currently looking at. The bizarre, fuzzy superposition of states that particles exist in before measurement could be the raw, unprocessed data waiting for a conscious observer, or the simulation's central processing unit to call for it and resolve it into a definite value, saving precious computational resources. The implications for our experience of time are equally profound. Glitches in the matrix, those fleeting moments of déjà vu or seemingly synchronicitous events, could be seen as minor rendering errors or hints of the code beneath the graphics. More significantly, if our reality is a simulation, then the laws of physics are not discovered but designed. The speed of light, the gravitational constant, the strength of the nuclear forces, these would be set by the programmers. The fact that our universe seems so finely tuned to allow for the existence of life could be interpreted not as a miraculous coincidence, but as evidence of deliberate design, or perhaps simply a selection effect. We can only find ourselves in a simulation that is capable of producing conscious beings to observe it. This paradox doesn't provide easy answers, but it radically reframes the questions, suggesting that the timeless regions we ponder might be the equivalent of commented-out code or a paused game state in a reality whose true nature is fundamentally computational. But if the black hole information paradox and the simulation hypothesis stretch our imagination to its limits, the next paradox brings us back to a phenomenon that is happening all around us, right here, right now, in the very emptiness we once thought was inert. We often think of a perfect vacuum as the ultimate nothingness, a void completely devoid of matter, energy, or activity. But quantum mechanics shatters this classical intuition, revealing that what we call empty space is in fact a seething, bubbling cauldron of raw potential, a dynamic arena where particles flicker in and out of existence in an endless, chaotic dance. This isn't just theoretical, it's a fundamental feature of our universe with real, measurable consequences, and it introduces a breathtaking paradox that the very ground state of reality, the quantum vacuum, is not a state of timeless stillness, but a frenzy of spontaneous activity where the arrow of time itself becomes blurred and undefined. This bizarre activity is driven by Heisenberg's uncertainty principle, a cornerstone of quantum theory which states that we can never precisely know both the energy of a system and the exact time that energy is measured. This isn't a limitation of our instruments, it's a fundamental property of nature. This uncertainty opens a door for the impossible to become possible, if only for an unimaginably brief moment. In the quantum vacuum, pairs of virtual particles, a particle and its antiparticle, can spontaneously pop into existence, borrowing energy from the nothingness itself. They exist for a time so short it's measured in units of Planck time, about 10 to the negative 43 seconds, before they inevitably collide and annihilate each other, paying back the energy loan and vanishing without a trace. This isn't a rare event. It's happening everywhere, all the time, trillions of times in the space of a single heartbeat, in every single cubic centimeter of so-called empty space. The great physicist John Wheeler captured the mind-bending implications of this with a powerful metaphor. He described the fabric of space-time at these tiny scales not as smooth and continuous, but as a quantum foam. Imagine the surface of the ocean on a calm day. From a distance, it looks like a smooth, glassy plain. But if you could shrink down to the size of a molecule, you would see a turbulent, frothing chaos of bubbles constantly forming and popping. Wheeler proposed that space-time itself is like this at the Planck scale. It's a churning, probabilistic foam where tiny wormholes might blink in and out of existence, and where the very concepts of before and after lose their clear meaning. In this foamy foundation, time isn't a smooth flowing river. It's more like a series of discrete, jittery frames in an old film reel, with gaps of indefinable chaos in between. This leads us directly to the heart of the temporal paradox. In our macroscopic world, time has a clear and irreversible direction, the arrow of time, defined by the increase of entropy. We remember the past and anticipate the future, but in the fleeting existence of these virtual particles, this arrow seems to vanish. A particle and its antiparticle are born together and die together in a perfectly symmetric event. There is no clear cause that precedes the effect. The pair simply emerges from the void and returns to it. In these micro-timeless zones, the progression of time isn't just slowed down, it's fundamentally non-linear and chaotic. For that infinitesimal moment, all possible timelines might coexist in a fuzzy superposition, challenging our most basic assumption that time must always flow smoothly forward. We can even witness the tangible effects of this quantum frenzy in a laboratory. The most famous demonstration is the Casimir effect. If you take two perfectly smooth, uncharged metal plates and place them incredibly close together in a vacuum, they will experience a faint but measurable force pulling them toward each other. Why? Because the space between the plates is so narrow that it restricts the kinds of virtual particles that can pop into existence there. The quantum foam outside the plates, however, is still bustling with activity. The greater pressure from the outside virtual particles literally pushes the plates together. This isn't a theoretical curiosity. It's a proven phenomenon, direct evidence that the vacuum is not empty, but is filled with a timeless energy that can exert a real physical force. This zero-point energy of the vacuum is a testament to the fact that at the most fundamental level, our universe is built upon a foundation of restless, spontaneous creation and destruction, a timeless dance of potentiality from which the illusion of continuous time emerges. Yet, even as we ponder the strange foam at the foundation of reality, we can look to the heavens and find a real-world laboratory where these extreme effects are not just microscopic flickers, but powerful, measurable forces shaping the destiny of entire stars. Imagine taking the entire mass of our sun and crushing it down into a sphere no wider than a city. A teaspoon of this material would weigh billions of tons. This isn't science fiction. This is the reality of a neutron star, one of the most extreme and fascinating objects in the universe, born from the fiery collapse of a massive star's core in a supernova explosion. The gravity on the surface of such an object is almost beyond comprehension, about 100 billion times stronger than the gravity we feel on Earth. And according to Einstein's theory of general relativity, Such an intense gravitational field doesn't just warp space, it warps time itself, creating a powerful and paradoxical slowing of time's passage for anyone or anything unfortunate enough to be near one. This phenomenon, known as gravitational time dilation, means that a clock placed on the surface of a neutron star would tick significantly slower than an identical clock far out in the emptiness of space. The difference isn't trivial. Time on the neutron star could be passing at less than half the rate it does for a distant observer. If you could stand on that unimaginably dense surface, your biological processes, your thoughts, your very experience of reality would unfold in slow motion compared to the rest of the universe. As you journeyed deeper toward the star's core, where the density and pressure become even more extreme, this effect would intensify, pushing closer and closer to a state of near timelessness where the progression of events grinds to a relative halt. This creates a stunning paradox, two realities unfolding at different speeds within the same cosmos. A single event, like the spin of the star, would appear to us as a regular, predictable rhythm, while for the fabric of space-time on the surface, that same rotation is happening within a drastically slowed-down frame of time. We can actually observe the consequences of this time warping in the behavior of pulsars, rapidly spinning neutron stars that beam radiation across space like a cosmic lighthouse. The timing of these pulses is phenomenally precise, rivaling the best atomic clocks on Earth. However, the intense gravity of the neutron star imprints itself on this signal. As the pulses of radiation climb out of the star's deep gravitational well, they lose energy and their frequency is shifted, an effect known as gravitational redshift. This is the direct, observable signature of time running slower at the source. Astronomers like Jocelyn Bell Burnell, who co-discovered the first pulsar, opened a window into this bizarre world. Her meticulous observations of these ticking celestial objects provided some of the strongest early evidence for the existence of neutron stars and, by extension, for the radical time-warping predictions of general relativity in action. To make this personal, consider a thought experiment with a pair of twins. One twin remains on Earth, living a normal life, while the other is sent on a mission to orbit a neutron star for what feels, to the traveling twin, like 1 year. Due to the incredible time dilation, the twin on the mission would age far more slowly. Upon returning to Earth, the spacefaring twin might have only aged a year, while decades or even centuries could have passed for the sibling left behind. This isn't just a theoretical puzzle. It's a dramatic illustration of how mass and gravity don't just tell objects how to move through space, they dictate the very flow of time itself. A neutron star is a perfect natural experiment, demonstrating that timelessness isn't an abstract concept confined to singularities, but a real gradient effect that becomes overwhelmingly powerful in the presence of extreme density, offering us a tangible glimpse into a reality where time is not absolute but deeply personally relative. But if the crushing gravity of a neutron star represents one extreme of time's flexibility, the next paradox invites us to consider an object that is its perfect mirror opposite, a concept so strange that it feels like it was pulled directly from the pages of a science fiction novel. Imagine a black hole in reverse. Instead of a cosmic drain from which nothing can escape, picture a cosmic fountain from which nothing can enter. This is the hypothetical white hole, a bizarre and stunningly counterintuitive object that emerges not from fantasy, but directly from the same equations of general relativity that so accurately describe black holes' gravity and the curvature of spacetime. In the pristine mathematics of Einstein's theory, the laws of physics are almost entirely time-symmetric. This means that if you take the equations that describe a process and mathematically reverse the direction of time, you often get another valid physical solution. A black hole which only absorbs has a perfect time reverse twin, a white hole which only ejects. The core of this paradox lies in the white hole's singularity. In a black hole, the singularity is a point of infinite density where time, as we understand it, is thought to cease. Matter and energy fall in, crossing the event horizon, and are lost to our universe. In a white hole, this process is flipped. The singularity would be a point of eternal emission, a source from which matter and energy spontaneously erupt outward. Anything attempting to cross into a white hole from the outside would be violently repelled. Nothing can ever enter. And just as time is believed to stop at the heart of a black hole, the singularity of a white hole might also be a place of timelessness, not as a final destination for infalling matter, but as an inexplicable origin point for outflowing energy, a place where the universe seems to be giving birth to something from nothing forever. The most fascinating and perhaps most telling aspect of white holes is that we have never observed one. While they are mathematically permissible, they appear to be physically forbidden by the second law of thermodynamics. A white hole would represent a massive decrease in entropy, a reversal of the universal trend toward disorder, essentially creating something from nothing in a way that seems to violate causality. This is why most physicists believe that while white holes are beautiful mathematical curiosities, they likely do not exist in our universe. However, their value is far greater than mere speculation. They serve as a crucial thought experiment, a tool that helps us stress test the boundaries of general relativity and understand the profound connection between time, entropy, and gravity. They force us to ask why the universe seems to have a preferred direction of time, and whether that direction is an absolute rule or just a local condition. To grasp the sheer weirdness of a white hole, consider a simple analogy. Picture a movie of a planet orbiting a star. Now play that movie in reverse. The planet will still orbit the star. The laws of gravity are time-symmetric, and the reversed movie still looks physically plausible. Now, picture a movie of a book falling into a black hole. It crosses the event horizon and is gone. Now, play that movie in reverse. What you see is a book spontaneously emerging from the black hole's horizon, flying out into space. This reversed movie is a visual representation of a white hole. It's a perfectly valid solution to Einstein's equations, but it depicts a sequence of events that feels utterly wrong to us because it violates our deep-seated intuition about cause and effect. The book comes out, but nothing went in to cause it. This is the white hole paradox in a nutshell, a universe that rigorously allows for time symmetry in its fundamental laws, yet seems to overwhelmingly prefer one direction of time in its actual events. This exploration of reversed time flow is more than just an academic exercise. It stretches our imagination about what is possible in the cosmos. It expands the concept of timelessness beyond mere stillness to include the possibility of time running backward, challenging the very linearity we take for granted. While white holes themselves may not be real, they illuminate the profound fact that our arrow of time, the relentless march from past to future, may not be written into the deepest laws of physics, but could instead emerge from the specific initial conditions of our universe, a one-way street built on a foundation that itself allows for two-way traffic. But if the bizarre concept of white holes challenges us with a vision of time in reverse, the next paradox brings us back to a principle that defines time's forward march in our everyday reality, a principle that seems so obvious, yet is one of the most profound mysteries in physics. This is the intimate connection between entropy and the arrow of time. We all intuitively feel that time has a direction. We remember the past but not the future. A cup of coffee cools down. It never spontaneously heats up on its own. A dropped egg splatters on the floor. The splattered pieces never leap back together to form a whole egg. This one-way street of cause and effect, of increasing disorder, is what we call the arrow of time, and it is almost universally governed by the second law of thermodynamics. The total entropy or disorder of a closed system always increases over time. The brilliant physicist Ludwig Boltzmann was among the first to make this connection in the late 19th century. He proposed that the reason we perceive time flowing in one direction is not because of some fundamental property of time itself, but purely due to statistics and the behavior of atoms. Imagine a brand new deck of cards perfectly ordered by suit and number. This is a state of incredibly low entropy. Now, if you shuffle that deck, you randomize it, increasing its disorder. The key insight is that there is only one way for the deck to be perfectly ordered, but there are an astronomical number of ways for it to be disordered. The universe, much like the deck of cards, started in a state of incredibly low entropy, a highly ordered, dense, and hot state at the Big Bang. Ever since, it has been naturally evolving toward states of higher probability, which are states of greater disorder. Our perception of time's arrow is simply our experience of the universe moving from a less probable past to a more probable future. This leads us to a stunning and counterintuitive conclusion. If entropy is what gives time its direction, then in any situation where entropy cannot increase, the arrow of time should vanish. Consider a system that has reached perfect thermodynamic equilibrium. Imagine a sealed, perfectly insulated box where the temperature is absolutely uniform everywhere inside. In this state of maximum entropy, no further energy can be extracted to do any work. No heat flows, no chemical reactions occur, no events of any kind can happen. It is a state of perfect, unchanging stillness. In such a box, if you were to somehow place a clock, its hands would not move. More profoundly, the very concept of before and after would have no meaning inside that box because nothing changes to mark the passage of time. The arrow of time, which depends on the increase of disorder, simply doesn't exist there. Time becomes irrelevant. Now, scale this idea up from a small box to the cosmos itself. Vast cosmic voids, the immense empty spaces between galaxies, are perhaps the closest things we have to these near-equilibrium systems. With matter spread incredibly thin and gravitational interactions minimal, change happens at an almost imperceptibly slow rate. In these near-timeless gaps, the arrow of time, while not completely gone, becomes incredibly faint. And at the most extreme end of the spectrum, consider the singularity at the heart of a black hole or the state of the universe at the hypothetical heat death. In these conditions, entropy is either undefined or has reached its maximum possible value. With no further disorder possible, no energy gradients to drive change, the universe or that region of it would be utterly static. Without change, there is nothing to measure, and without measurement, time loses all meaning. It's not that time stops, it's that the concept itself evaporates. This forces upon us one of the most fundamental questions we can ask about reality. Is time real? Or is it merely a useful illusion, an emergent property that arises from the statistical behavior of countless particles? If the flow of time is contingent upon the increase of entropy, then time is not a primary stage upon which the universe plays out, but rather a secondary phenomenon, a side effect of the universe's journey from order to disorder. In regions where that journey has ended, time simply ceases to be. This paradox doesn't just belong to the realm of theoretical physics. It touches on philosophy and our very perception of existence. It suggests that our lived experience of a flowing, linear time is a narrative we construct, a story told by the inevitable rise of disorder, and that the true underlying reality might be far more strange and timeless than we can possibly imagine. But if the smooth, continuous time of our daily experience feels like an unshakable truth, the next paradox shatters that illusion into a billion tiny pieces, proposing that time itself might be pixelated. This is the radical vision of loop quantum gravity, a bold theoretical framework that suggests the very fabric of spacetime is not a smooth, continuous sheet as Einstein described, but is instead woven from a network of incredibly tiny, discrete loops. Think of it like a digital photograph. On your screen, the image appears smooth and seamless, but if you zoom in far enough, you'll see it's actually composed of individual pixels. Loop quantum gravity argues that reality itself has a resolution, and at the smallest possible scale, the Planck scale spacetime reveals its fundamental graininess. In this view, the dimension of time is not a flowing river but more like a flipbook, a rapid succession of static frames that creates the illusion of smooth motion. At the heart of this theory is the concept of a smallest possible unit of time, known as the Planck time. This is an almost unimaginably brief interval, about 10 to the negative 43 seconds. According to loop quantum gravity, time cannot be divided into units smaller than this. There is no in between one Planck moment and the next. This means that below this scale, the very concept of temporal flow has no meaning. Time doesn't just slow down, it becomes granular, a series of indivisible moments. In the gaps between these moments, there is no time at all. This creates a fundamentally timeless foundation for reality, a substrate where change is not continuous but happens in discrete, tiny jumps. Our experience of a smoothly flowing now is then a large-scale approximation, an emergent property that arises from the collective behavior of these countless quantum grains, much like the smooth flow of a movie emerges from the rapid projection of individual still frames. Theorists like Carlo, Rovelli have been at the forefront of developing this idea, weaving together the principles of quantum mechanics and general relativity. Rovelli suggests that time is not a primary ingredient of the universe, but something that emerges from the quantum interactions and relationships between events. In his relational view, time doesn't exist on its own. It only exists because things change relative to each other. Without change, there is no time. Loop quantum gravity provides a potential physical basis for this by proposing a universe built from a spin network, a web of these discrete loops with quantized areas and volumes. The evolution of this network from one state to another creates a natural, granular sequence that we interpret as the passage of time. In this framework, the entire history of the universe could be seen as a vast, evolving network where what we call time is just the numbering of these distinct steps in the evolution of the geometry of space. To truly grasp the strangeness of this, consider a powerful analogy. Imagine you are watching a stream of water flowing from a tap. It appears as a continuous, unbroken column. But we know that water is actually made of molecules. If you could slow down your perception to an incredible degree, you would see that the stream is not perfectly continuous. It is a series of individual H2O molecules passing by one after another. Loop quantum gravity proposes that time itself is like that stream. Our normal perception shows us a smooth flow, but at the most fundamental level, reality is made of discrete moments. There is no smooth transition from one moment to the next. The universe literally jumps from one quantum state to another, with nothing in between. This means that what we perceive as the continuous flow of time is actually a cosmic illusion, a trick of the scale at which we live our lives. This perspective offers a breathtakingly elegant resolution to the problem of the Big Bang singularity. In classical general relativity, the beginning of the universe is a point of infinite density where the laws of physics break down. But in loop quantum gravity, because space and time are granular, they cannot be compressed to an infinitely small point. There is a smallest possible size, a smallest possible volume. This means that if we rewind the cosmic film back to the very beginning, we wouldn't find a singularity. Instead, we would find a previous cosmic phase, a big bounce where a previous universe contracted to a tiny size before quantum gravity effects caused it to rebound into our expanding universe. In this model, the Big Bang was not the absolute beginning of time, but a transition from a prior state, a moment where the timeless, granular fabric of space-time underwent a dramatic transformation, giving birth to the time we now experience. Yet, even as we explore the granular nature of time at the quantum scale, we must turn our attention to a period in our own cosmic history when the entire universe underwent a transformation so rapid and so profound that it challenges our very understanding of temporal flow. This is the theory of cosmic inflation, a breathtaking idea that proposes that a fraction of a second after its birth, the universe experienced a burst of hyper-expansion, inflating from a subatomic speck to something astronomically large faster than the blink of an eye. During this inflationary epoch, the very fabric of spacetime was stretched at an exponential rate, and in the heart of this frantic expansion, some models suggest that time itself may have lost its conventional meaning, existing in a strange, undefined state before settling into the steady rhythm we know today. The concept of inflation was first proposed by physicist Alan Guth to solve several major puzzles in cosmology, such as why the universe appears so remarkably uniform in all directions. His revolutionary insight was that a peculiar energy field known as the inflaton field could have briefly dominated the early universe. This field would have been trapped in a false vacuum state, a condition of incredibly high energy that is not its true stable minimum. Think of it like a ball resting precariously on the lip of a tall, steep hill. While it's up there, it possesses a tremendous amount of potential energy. In the cosmological context, this energy had a repulsive gravitational effect, causing space to expand at a staggering rate, doubling in size every tiny fraction of a second. It is within this false vacuum state that we encounter a profound temporal paradox. In this incredibly high energy environment, the properties of the quantum fields were so extreme that the standard distinction between space and time may have broken down. The frantic expansion was so rapid that it could have effectively stretched out any initial timeline, smoothing it to the point of irrelevance. Furthermore, the intense quantum fluctuations rippling through the inflaton field would have been so dominant that they could have overwhelmed any clear classical notion of a temporal sequence. In this view, the inflationary epoch wasn't just a period of rapid change in time. It was a phase where the concept of time itself was not yet well defined, a primordial, chaotic state where the clock of the universe had not yet started ticking in a coherent way. The transition out of this phase is what ultimately gave birth to time as we experience it. Eventually, the inflaton field tunneled or rolled down from its false vacuum peak to its true, stable minimum, a process called reheating. As it did, it released its enormous pent-up energy, flooding the universe with the hot plasma of particles and radiation that would eventually form everything we see. It was at this moment of decay, this cosmic phase transition, that the universe settled into a state where the laws of physics as we know them, including a clear, linear arrow of time, came into sharp focus. The end of inflation marked the true beginning of our conventional cosmic timeline, the start of the hot Big Bang. This suggests that our universe's history did not emerge from a singularity of infinite density, but from a prior, timeless state of inflationary energy, a period of unstable potential where time was not yet the fundamental framework for reality. This elegant model provides a powerful link between the timelessness of quantum gravity and the time-bound universe we inhabit. It connects the birth of time directly to a specific cosmological event, the decay of the inflattened field. This paradox forces us to reconsider the very origin of everything, suggesting that time is not an eternal backdrop but an emergent property that flows out of a more fundamental, and perhaps timeless, state during the universe's frantic initial expansion. It is a cornerstone of modern cosmology, offering a compelling narrative that stretches from a mysterious, timeless beginning to the rich, temporal cosmos we call home, all within the first infinitesimal moments of existence. And just as we explore the universe's grandest scales, we can turn our gaze inward to a phenomenon every single one of us has experienced: the strange and fluid nature of time within our own dreams. While you sleep, your brain becomes a master illusionist capable of crafting entire lifetimes of experience in what a clock on your nightstand and would measure as mere minutes. This isn't just a curious trick of the mind. It's a profound demonstration that our perception of time is not a direct readout of the external world, but a fragile, malleable construction built by our own neurology, one that can be stretched, compressed, or even completely suspended. The stage for this temporal distortion is primarily set during REM sleep, the phase most associated with our most vivid and narrative-driven dreams. During REM, the brain undergoes a fascinating shift. The prefrontal cortex, the region responsible for logic, executive function, and our critical sense of time, shows significantly decreased activity. Meanwhile, the limbic system, the emotional center of the brain, and the visual cortices light up with intense activity. This neurological cocktail creates a perfect storm for time perception to go completely off the rails. Without the prefrontal cortex to anchor us to a linear timeline, the dream world operates by its own rules, where scenes can jump cut, narratives can loop, and the duration of events becomes entirely untethered from the steady tick of a clock. This creates experiences that feel eerily similar to the cosmic timelessness we've been exploring. Many people report dreams that feel like they lasted for hours, days, or even years, only to wake up and find that only 20 minutes have passed. The opposite can also happen. A long, complex dream can feel like it was over in an instant. For lucid dreamers, those who become aware they are dreaming and can sometimes exert control, the effects are even more pronounced. They often describe moments of incredible clarity within a dream where everything seems to freeze, a state of perfect, suspended animation where thought continues, but the dreamscape itself becomes a static, timeless tableau. In these moments, the dreamer touches a state of consciousness that mirrors the timeless singularities and static universes of physics, all generated from within the confines of their own skull. What makes this so powerful is that it bridges an immense gap. The timeless regions inside black holes or at the birth of the universe are abstract concepts, understood through complex mathematics and observed only indirectly. But the timelessness of a dream is immediate, personal, and universally accessible. It proves that the feeling of existing outside of time isn't just a theoretical possibility, it's a fundamental capacity of the human brain. This suggests that our standard experience of linear time is just one mode of operation for our consciousness, a useful setting for navigating the physical world, but not the only one available. By simply closing our eyes each night, we journey into a personal cosmos where the rules of time are optional, offering a tiny, intimate glimpse into the kind of reality that might exist in those far-off, mysterious regions of space. But if the frantic energy of the early universe and the distorted time of our dreams represent two very different extremes, there exists a region of profound stillness right in the middle, in the vast and empty spaces between the glittering strands of the cosmic web. Imagine the universe not as a uniform soup of galaxies, but as a magnificent sponge. The dense filaments and clusters of galaxies are the solid material, but it's the holes, the immense, sprawling cosmic voids, that make up most of the volume. These are not small, empty patches. They are staggering in their scale, some spanning hundreds of millions of light-years across, containing almost no galaxies, no stars, and very little matter. In these near-perfect vacuums, the gravitational pull is so weak it's almost non-existent, and the fabric of space-time is as flat and undisturbed as a calm sea on a windless day. It is here, in these deserts of nothingness, that we find a paradox of timelessness born not from extreme force, but from profound isolation. Within one of these voids, the local experience of time is arguably the most pure and undistorted in the entire universe. Without massive objects like black holes or galaxy clusters to warp spacetime, a clock placed in the heart of a void would tick at almost the same rate as a clock in the absolute emptiness of intergalactic space, very close to the ideal rate predicted by the theory of relativity. There is no significant gravitational time dilation here. If you could somehow find yourself floating in this endless, dark expanse, your personal experience of time would be as regular and steady as it could possibly be. Yet, this very isolation and emptiness creates a different kind of timelessness on a grand structural scale. It's a timelessness of disconnection, where the cosmic distances and the void's sheer emptiness conspire to break the chain of causality that weaves the universe together. This leads us to the true heart of the paradox. For two events to be connected in any meaningful way, for a cause to lead to an effect, information must be able to travel between them. That information, whether it's a flash of light, a gravitational wave, or any other signal, is bound by the universe's ultimate speed limit, the speed of light. Now consider two galaxies sitting on opposite sides of a giant void. The distance between them is so astronomically vast that even light, traveling for billions of years, would still be crossing that empty chasm. An event in one galaxy, like the explosion of a star, simply cannot be known about or have any influence on the other galaxy for an almost unimaginable length of time. For all practical purposes, from the perspective of either galaxy, the other exists in a separate, disconnected timeline. They are islands of causality adrift in a sea of stillness, each unfolding its own history in effective isolation from the other. This isn't just a theoretical idea. Astronomers actively study these voids to understand the large-scale structure of the universe. By mapping their sizes and distributions, they can trace the gravitational forces that have shaped the cosmos since the Big Bang. These voids are not completely empty. They contain a sparse population of isolated, void galaxies, which often evolve differently than their cousins in denser clusters, starved of the interactions that drive galactic evolution elsewhere. These galaxies are living their lives in extreme slow motion compared to the bustling metropolises of galactic clusters, further emphasizing how location within the cosmic web dictates a completely different experience of time and change. The void is a place of profound quiet, where the universe's story unfolds not in a single, unified narrative, but in countless isolated chapters, separated by gulfs of space so vast they become gulfs of time. But just as we contemplate the profound isolation of cosmic voids, our journey takes an even more spectacular turn, pushing past the very boundaries of our own universe into the unimaginably vast arena of the multiverse. Imagine our cosmos not as a solitary island of reality, but as one bubble in a vast, frothing sea of cosmic foam, where countless other universes, each with their own unique physical laws and histories, are constantly bubbling into existence. This is the breathtaking landscape of eternal inflation, a theory that suggests the rapid expansion of space that fueled our Big Bang never truly stopped everywhere, but continues in a wider background meta-universe, giving birth to an infinite number of these pocket universes. And in this grand, chaotic ensemble, these cosmic bubbles don't always remain politely separate. They can sometimes drift, expand, and inevitably collide with one another. When two such bubble universes meet, the result would be an event of almost unimaginable scale and violence, a collision between two entire realities. At the boundary where their expanding walls meet, the fundamental laws of physics from each universe would interact, clash, and potentially merge. This is where we encounter a profound temporal paradox. Each of these colliding universes might possess its own unique arrow of time, its own direction of temporal flow, defined by its own internal increase of entropy. What happens when two such arrows, potentially pointing in completely different directions or even operating under different dimensional rules, slam into one another? The interface between them could become a zone of pure chaos, a cosmic no-man's land where time is not just slowed or warped, but becomes completely undefined. The very concepts of before and after could break down at this collision boundary, creating a region of genuine timelessness where the sequential order of events is scrambled beyond recognition. The consequences of such a collision are as wild as they are speculative. One possibility is that the impact could act like a cosmic reset button for one or both universes involved. The immense energy released could trigger a new period of inflation within a bubble, effectively restarting its cosmic clock and erasing any prior history. Alternatively, the collision might not destroy the universes but stitch them together, creating a bizarre bridge, a cosmic scar, where the laws of physics are a hybrid of the two original sets. In this bridged region, time might flow in a loop, or it might not flow at all, existing as a permanent, static wound in the fabric of space-time. For any hypothetical observers inside one of these universes, evidence of such a collision might be imprinted on the sky. Some cosmologists have even searched for odd, circular patterns in the cosmic microwave background radiation, the afterglow of our own Big Bang. That could be the faint, cooled remnant of a long-ago collision with another bubble universe, a fossilized bruise from a fight between two realities. This idea pushes the concept of timelessness to its ultimate extreme, beyond the confines of a single cosmos. It suggests that timeless regions aren't just hidden inside black holes or at the end of time, but could exist at the frontiers where entire universes meet. These interfaces would be places where causality itself becomes tangled, where an effect in one universe might inexplicably precede its cause from another, violating all our intuitive understanding. It's a vertigo-inducing thought that encourages us to think not just beyond our planet or our galaxy, but beyond our entire reality, contemplating a multiverse where time is not a universal constant but a local variable, and where the most profound silence, the absolute absence of time, can be found in the violent, world-shattering collisions between worlds. But if the violent collisions of entire universes represent a macro-scale, timeless chaos, the next paradox brings us back to the delicate, microscopic process that might be responsible for creating the steady flow of time we experience in the first place. This is the fascinating concept of quantum decoherence, a mechanism that explains how the bizarre, fuzzy world of quantum possibilities sharpens into the definite, concrete reality we perceive. At its heart, decoherence tackles the mystery of the quantum measurement problem, why we see particles in specific locations with definite properties, rather than the ghostly superpositions the math of quantum mechanics describes. The answer appears to lie not in conscious observation, but in relentless and unavoidable interaction with the environment. Every single particle is constantly bumping into, interacting with, and being influenced by the countless other particles around it. This ceaseless conversation with the environment acts like a constant measurement, forcing quantum systems to shed their fuzzy superposition states and pick a single classical outcome. The profound connection to time emerges when we consider what happens in the absence of these interactions. Imagine a single, perfectly isolated quantum system, perhaps an electron placed in a magical box that shields it from any contact with the outside universe. In this pristine isolation, the electron could happily exist in a superposition, spinning both clockwise and counterclockwise simultaneously. Without any environmental interaction to force a choice, its wave function remains coherent, a blend of all possibilities. In such a state, the clean, linear progression of time we rely on becomes blurred. There is no clear sequence of definite events because no specific outcome has been selected. The system exists in a kind of timeless potentiality where the future remains open and unfixed. It is only when the isolation is broken, when the environment inevitably interacts with the system, that decoherence occurs. The superposition collapses, a specific outcome is chosen, and that event is added to the timeline of the universe. In this view, the flow of time is not a fundamental river, but a cascade of countless decoherence events, each one nailing down a specific reality from a sea of possibilities. Physicists like Wojciech have been instrumental in developing this elegant theory. He and others describe the environment as a kind of witness, constantly recording information about quantum systems through interactions. This process, which he calls einselection or environment-induced superselection, is what defines the familiar properties of the classical world. It explains why we see tables and chairs in specific places and not in superpositions. Crucially, this process also provides a powerful explanation for the arrow of time. Decoherence is overwhelmingly likely to happen in one direction, from a pure, coherent quantum state to a mixed classical state. This irreversible loss of quantum information into the environment mirrors the increase of entropy, providing a quantum mechanical foundation for time's one-way direction. The universe started in a highly ordered, low-entropy state, and decoherence is one of the key mechanisms driving it toward higher entropy and greater definiteness. To grasp this, consider a simple but powerful analogy. Imagine a pristine, still pond representing a perfectly isolated quantum system. You drop two stones into the pond at different points. Initially, the ripples from each stone expand outward in perfect, coherent circles. If you could freeze this moment, you would see a clear interference pattern where the ripples meet. This is the quantum superposition. But now, reality sets in. A gentle breeze blows across the water's surface, a leaf falls in, a fish jumps. These are the environmental interactions. They disrupt the perfect, clean ripples, churning the water into a complex, chaotic mess of overlapping waves. The delicate interference pattern is destroyed, and the pond's surface becomes a single, definite, choppy reality. The transition from the clean, coherent pattern to the messy, definite reality is decoherence. It didn't require a physicist with a measuring device. It happened naturally through interaction with the environment. This is how our universe works. The initial coherence of the Big Bang has been constantly and irreversibly decohered by the trillions upon trillions of interactions between particles, steadily building the definite timeline we call history. This leads to a stunning conclusion about the nature of reality. Without decoherence, the universe would remain a timeless, fuzzy haze of potentialities. All possible histories and all possible futures would exist simultaneously in a vast, unchanging quantum tapestry. there would be no then and now, no cause and effect, no story to tell. It is the relentless process of interaction and measurement decoherence that crystallizes this potential into a single, flowing timeline. Time, in this view, is not a fundamental dimension woven into the cosmos, but an emergent property that arises from the relationships between quantum systems and their environments. It is relational and participatory, built moment by moment through the countless conversations that make up the universe. This paradox beautifully bridges the gap between the quantum and the classical, showing us that the steady tick of the clock is the grand, collective result of an infinite number of tiny quantum decisions happening all around us all the time. For thousands of years, long before telescopes or quantum equations, humanity has been grappling with the concept of timelessness, not in laboratories, but in the sacred spaces of temples, churches, and meditation halls. Across virtually every culture and spiritual tradition, we find a strikingly consistent theme: the description of a realm or a state of being that exists completely outside the relentless flow of time. In Christianity, God is often described as eternal, not in the sense of lasting forever in time, but as existing beyond time itself, in a perpetual, unchanging now where past, present, and future are simultaneously present. This isn't a place you go to after a long life. It's a fundamental aspect of the divine nature, a state of pure being without becoming. This vision of a timeless reality echoes powerfully in Eastern traditions as well. In Hinduism, the ultimate reality, Brahman, is described as Sat Chit Ananda, eternal existence, consciousness, and bliss. It is the timeless, unchanging foundation upon which the illusion of the changing, temporal world or Maya is projected. Similarly, the Buddhist concept of nirvana is not a heavenly paradise in time, but the extinguishing of the fires of craving and aversion, which is also an escape from the cyclic suffering of samsara, the endless wheel of time-bound birth, death, and rebirth. To achieve nirvana is to step out of the stream of time altogether, into a state of peace that is unconditioned and eternal. These are not merely philosophical speculations, they are the culmination of profound mystical experiences, reported by contemplatives and meditators who describe states of consciousness where the sense of a separate self and the ticking clock simply dissolve into a vast, undifferentiated awareness. What is truly fascinating is how these ancient spiritual intuitions form a remarkable parallel to the timeless regions modern physics has begun to map mathematically. The theologian's description of a God beyond time resonates with the physicist's block universe, where all of history is equally real. The mystic's experience of the eternal now finds a strange cousin in the quantum vacuum, where particles flicker in and out of existence in timeless intervals. The Buddhist's release from cyclic time mirrors the cosmologist's model of a cyclic universe, with its timeless moments of bounce between eons. It's as if the human mind, through both inward contemplation and outward scientific exploration, has been circling the same profound mystery from two completely different directions. This convergence is not a coincidence. It speaks to a deep and enduring human yearning to understand our place in the cosmos. The paradox here is that our most advanced scientific theories and our most ancient spiritual wisdom are both pointing toward the same mind-bending possibility, that the time-bound world we experience with our senses, with its beginnings and endings, its causes and effects, might be a kind of shadow or projection of a deeper, timeless reality. This doesn't prove the tenets of any particular faith, but it does validate the human impulse behind them. It suggests that the quest to understand time is not just a technical puzzle for physicists, but a fundamental part of the human condition, a journey that spans disciplines and millennia, enriching our appreciation for the profound mystery we are all a part of. We have ventured to the very edge of understanding, from the crushing depths of black hole singularities to the seething quantum foam of empty space, and even into the silent, eternal now of our own consciousness. We've seen how time is not a rigid, universal constant, but a fluid and relative experience emerging from deeper physical processes like the increase of entropy or the decoherence of quantum possibilities. These explorations force upon us profound questions that straddle the line between physics and philosophy. Is time real, or is it the ultimate illusion? Does the universe have a history if there is no one to observe it? And what does it truly mean to exist in a cosmos where the past, present, and future might all be equally real? These ideas are not just academic curiosities. They challenge us to rethink our entire relationship with reality and our place within it. They invite us to consider that our linear cause and effect experience of life might be just one narrow perspective on a far grander, more mysterious whole. The quest to understand timelessness, whether through the equations of general relativity or the introspective peace of meditation, is ultimately a quest to understand the very fabric of existence. As the great astronomer Carl Sagan once reminded us, somewhere, something incredible is waiting to be known. That something might not be a distant planet or a new star, but a deeper layer of reality itself, waiting to be uncovered just behind the veil of our perception. So we leave you with this final thought to ponder. How does this journey through timelessness change your view of your own life? Does the possibility that all moments might be eternally present make the present moment more precious or less? Does it make our struggles and joys feel more significant or like mere notes in a vast, eternal symphony? We encourage you to carry these questions with you. Let them expand your mind and